is track 1 mono.
Thank you very much. I'm honored to open this conference. AI exploded into our life with the introduction of the deep learning architecture and revolutionized our life in just about every facet. When lay people talk about AI nowadays, they mostly refer to the large language models such as GPT or Claude. But I'm sure you all know that AI is a major engine in lots of domains, large and small. It is a major tool in science and technology. It can be used as a decision maker in a wide variety of social and economical contexts, for medical attention, through job interviews, to getting loans, and indeed, it is a major cultural, economical, and may I even say, scientific actor. Clearly, AI is a major revolution that is changing our life in a fundamental way. It's, as industry people say, it's a huge disruption. The description so far reflects only some of the potential benefits that we may gain from the AI revolution. But given its immense abilities and its presence in almost all aspects of life, and more so, given its potential future development, it may also pose very serious challenges to our society. This is the topic of our meeting here now. We are going to hear from 4 highly distinguished speakers some of their thoughts on AI and society, Renaissance and doom. These speakers are Christopher Pissarides, a 2010 Nobel laureate in economics, Michael Levitt, a 2013 Nobel laureate in chemistry, Michael I. Jordan, 2022 World Laureate Association Prize in Computer Science or Mathematics, and Whitefield Diffie, 2015 Turing Award winner. We will start with Professor Christopher Pissarides. Please, keynote.
Thank you very much. It's a great honor for me to be opening the sequence of keynotes in this forum. The topic I've chosen is economic growth and in the age of AI. Now, the age of AI is bringing a lot of structural changes to the economy, which necessitate worker transitions across jobs. Now, these transitions are a necessary part of economic growth. We need them, otherwise we don't get economic growth. And as Joseph Schumpeter wrote as early as 1942, they are part of a process of creative destruction of old and established work methods, which are replaced by new methods as technology advances and creates new work opportunities. And this, by the way, was the subject matter that was awarded by the Nobel Prize in Economics, the current one, 2005. There are many things that we have learned from economic history that help us understand what kind of creative destruction robots and AI might bring to the economy. And this is what I propose to focus on in this talk today. In other words, on what changes are we seeing in the economy and what are we likely to see. Now, first, what we learn from economic history is that AI, and I'm using this collectively to include both modern robots and artificial intelligence, is transforming work, is not eliminating it. Whether people work or not is their choice, not dictated by technology. And for better or worse, we like to work as human beings. John Maynard Keynes, one of the greatest minds in economics, as early as 1930 warned that we may have the choice to give up most of our work 100 years from his time of writing. That's 4 years from today. But he claimed that we're so used to work that if we do, we might all end up suffering from chronic depressions, So we should think very carefully how to do it, if we are going to do it. I am on his side. We like to work, and AI is not going to change this in the foreseeable future. It's ironic that the people who speak frequently about not having to work because of AI are also the greatest workaholics that you are likely to meet, from Elon Musk down. And psychologists remind us that one of the puzzles they encounter when they think about economics is why very rich people work so hard. The second thing we learn from economic history is that economic transitions take a very long time. China's transformation is a modern economic miracle. Yet, 45 years later, the country is still a middle-income country on the World Bank definitions. Eastern Europe started transitioning to the technologies of the European Union 35 years ago, but with very minor exceptions, all formerly planned economies have not yet caught up even with the poorest members of the European Union in the European South. So don't expect quick miracles from AI. Many people are saying that modern technologies are spreading incredibly fast. Look at the smartphone or ChatGPT. But what has their impact on productivity and growth been? Most economists will agree that although 80% or more firms in advanced economies are already using them, their impact on productivity has been minimal. And despite the hype with new apps and their spread, none gets even close to having the impact that Henry Ford and his electric assembly lines had on horses and their keepers. From 130,000 working horses in New York City in 1910, only 30,000 remained by 1930. And unlike today's AI transformations, that one had a huge impact on productivity. Third, we learned that new technologies destroy some jobs, create others, and bring changes to the work practices of most jobs. AI is no exception. Somehow, well-functioning economies find a way of adjusting without creating what is sometimes called technological unemployment. So don't expect to see AI-induced unemployment. The most likely impact of AI on jobs is transition within companies, as roles and people use AI tools to augment their capabilities and production processes. Now, AI technologies say that we already know a lot about AI to make a real difference to how we work. So why are we so slow to transition to the world of AI? And can we do anything about it? Whichever way you look at AI and work, you will encounter frictions to the smooth functioning of the economy. This is a term that describes factors that slow down the adjustment to new situations and sometimes don't allow us to adjust at all. What are these frictions in the case of AI? I don't have time to tell you what we can do about them, so I'll just outline the problems in what remains of my time. First, there is need for new investments, as the capital that companies need to work with AI is new. Large capital investments are difficult to bring about as they require long-term commitment of a lot of funds. With the uncertainty that is present today about AI, firms are reluctant to commit to long-term investments, a problem that may not be so serious and prohibitive in the United States and China, but it is the main barrier in Europe and elsewhere in the global economy. This is not the only investment that is needed. Investments in infrastructure might be a bigger friction. Infrastructure includes good connectivity, much larger energy supplies to power data centers than we now have, and free access to the latest apps. It's been argued that China's prominence in the development of AI has a lot to do with the open source generative AI that it pioneered with DeepSeek, in contrast to ChatGPT, which preceded it. This was a theme at the recent Davos Economic Forum, for example. Frictions that slow down AI adoption are important in labor markets too. Workers need to retrain and upskill with help from their employers, governments and educational institutions. All these need to reform to satisfy modern AI needs, but reform is slow. The uncertainty that prevails about the skills needed is an important factor here. At the recent World Economic Forum meetings in Davos, there were several discussions about the skills needed, but there did not seem to be consensus. In my view, the implication of this uncertainty is that we should not be specializing too much because needs might change. But without specialization, as our founder Adam Smith said 250 years ago, we might miss on productivity gains. So in a sense, we are stuck in this uncertainty equilibrium that we now have. So to conclude, what can I say about AI and growth? The best I can do is to say to the scientists, keep inventing, but pay attention to technologies that augment human labor. These technologies are the ones that have the best chance of improving productivity. AI agents are a good example of augmentation, but I have doubts about AGI, general I, if and when it comes. To government, I should say invest in energy sources and infrastructure quickly and urgently. And to company directors and their workers, I say be patient. These changes take time, but try to learn new ways of working that accommodate AI technologies, because there is a lot that can be done with them once they mature and get established in our working routines. Thank you very much. Please.
Our next speaker, I had actually the pleasure of sitting by him yesterday in dinner, is Michael Levitt, who is a 2013 Nobel laureate in chemistry. Michael, please.
Thank you so much, Asha. So I actually have slides, and Professor Pissarides talked about friction, and I'm talking here about friction-free, thought-filled exploration of ideas. I've used AI for most of my life as a computational biologist and chemist, and when large language models became available, I was a very, very early adopter. Right now, I would say that my work is almost 90% driven by AI. So basically, AI relies on the fact that science is actually driven by randomness. People think that scientists actually know what they're doing, but largely scientists start out with a random idea. I should also have said that I'm not interested so much in AI as a subject in science, but AI for scientists. I believe that AI really starts at home by helping every scientist become better at biology, data, physics, and chemistry, and molding all of these things together. So science doesn't really start with a clear question. It typically starts with a vague cloud that we look at, we stare at, we do experiments on, we ask questions of, and slowly the ideas emerge. And in doing this, we often take false paths. Most scientists will stress how often they're wrong compared to how often they're right. And that's because if you do something very difficult, you're like an ant searching for food, and most of the time you fail. Where AI can really help is make the exploration much more quick. So you get to your failures more quickly, and therefore can explore many, many more ideas. And this is true both in computational work, in theoretical work, and also in experimental work. Since failure is typically the rate-limiting step, and if we can reach the failures, we can't avoid the failures. We avoid the failures by doing something easy. If we're going to do something difficult, we have to expect to fail. So basically, AI has this ability, to really make it much quicker and easier to test our ideas. And this is important. It's important to realize that right today, where AI has achieved a massive speed up, is that a computer program that would take a good programmer 2 days to write is written in 5 seconds. That is typically, I think, 10,000 times speed up. 10,000 times is a massive speed up, and this means that anybody doing computer work is driven by something that is 10,000 times faster. And this is really remarkable. And it's no longer a question of actually writing code, but simply looking at results and seeing if they make sense. So basically, error becomes expected. Error has suddenly become much cheaper. It's no longer such a serious problem. Okay, so basically, we're often wrong, and therefore we need to be able to check these errors more quickly, but also methods no longer matter. I can write computer programs in areas that I have very little knowledge about, because the computer has access to all of these different methods. I can explore areas of science about which I have very little knowledge, because you can immediately get into a new area. So basically, language, method, and library barriers are just falling away in science. So basically, science, for me, AI, over the last 3 years, in 2003, AI was a helper. 2004, an assistant. And now I would say that AI, for me, is a real colleague, a good colleague. And this is a remarkable change. What it's going to be next year, maybe it will be my boss. I'm not really sure. So essentially, the takeaway is that anyone who plays with AI will become smarter, more efficient, more capable. This is a message I've been giving at meetings, and many of you have heard me say exactly the same thing 2 years ago in Dubai, 2 years ago in China, and so on. But it really is a message that I'm absolutely convinced by, because basically we'll have a higher effective IQ, because we can do faster research and get more ideas. Thank you all for your attention.
Thank you, Michael. Our next keynote speaker is Michael I. Jordan, the World Laureates Association Prize in Computer Science or Mathematics. Please.
Thank you. I've been working in AI for about 40 years, and it's always a pleasure to talk to others about their view on the topic. We never called it AI in our field. We always called it machine learning. And AI, unfortunately, was brought back from the death throes and is being used for this technology. And it's not very accurate as a terminology. And I want you to learn a little bit about that in my talk. So first of all, if you interact with ChatGPT or a language model, and you ask a question about mathematics or physics, you might get an answer that comes from one of the people in this room, something they wrote back in the past, or their students. If you ask about hip-hop music in Brooklyn, you may get an answer from some other crowd of people, or restaurants in Shanghai, et cetera, et cetera, et cetera. When you're interacting with ChatGPT, you're really interacting with all of humanity, billions of people who've contributed to it. It's a collective. And not only are you interacting with it, but billions of people are interacting with it as well. It's a collective on both sides, the producer and the consumer side. The systems that are being built with these things are not simply a secretary to help you think. They're also underlying the world's logistics chains, the world's healthcare systems, the world's transportation systems. So they are large-scale networks composed of many, many stakeholders in many, many pieces. Data is flowing among these pieces, decisions are being made, things are being shared, there's collusion, there's cooperation, and so on. So as that diagram suggests up there, we're going to all be immersed, we already are, in a system with many, many humans and many, many pieces of AI. It's not that there's a super intelligence on a hill that we all consult. We're all enmeshed together in this thing. So in this diagram there, the AI is in the overall network. It's not simply in a box. Now, if you take a collectivist point of view, you're already in the world of microeconomics. So if you ask, where's the AI? It's also in the connections. It's also in the economy that arises when you put all these pieces together. And so a new version of AI needs to be built that's not simply data analysis and prediction. It's also microeconomics. Now, when you think this way, you start to realize there's some serious problems of bias. If I'm enmeshed in a network and data is flowing at me from other people and other entities, they may have their own agenda. They may be strategic. The data may be false. Even if it's not false, it may be biased severely. Here's an example that we've studied in our group, AlphaFold. You all know it's extremely accurate, major progress. It is a foundation machine learning model, or AI, if you choose to call it that. Now, here is an example, briefly, I'm not going to get into details, of a study that was done in 2004, studying whether proteins who have quantum fluctuations also are used in the cell. They're active in the cell. Quantum fluctuations often means you have a strand hanging off of the protein. It didn't fold, so you might think it's a bad protein, but it turns out it's probably used in the cell. When this was first studied, there were about 10,000 entities in the protein data bank, and there was not enough power to reject the null hypothesis. 20 years later, instead of using data, AlphaFold output, of which there were 200 million proteins, was used to replace it, and you rejected the null hypothesis completely convincingly. Very small error bar. The problem was it was extremely biased. So on this slide, you'll see a statistician slide, mine, where on the x-axis you have a certain statistic. If the value is 1, there is no association between quantum fluctuation and phosphorylation. The gold little region there is a confidence interval coming from AlphaFold. It's very, very narrow. It's very sure of itself. But the truth is the dashed line there. It is not covering the truth at all. And we've seen this in domain after domain. We have a paper in Science that shows this. A classical statistical confidence interval is the gray region based on all the data actually in the protein data bank. Advance in statistics that allows you to correct confidence intervals from things like foundation models that are incorrect, overly confident. It moves it over to provably cover the truth and makes it a little bit broader. It's honest. The message here is that foundation models may be very good overall, but they can be inaccurate if you're a problem. You shouldn't trust them completely. You should use them, but not trust them. And here's the reason why this happens in AlphaFold. Here's an example of a prediction on the left and the actual structure on the right. It completely missed the quantum fluctuation. Why? Well, because in its data set, there wasn't many examples of this. Why? Well, because scientists are mostly interested in being on the boundary of knowledge. On the boundary of knowledge, there's not so much data. It's very good at all of the past knowledge and poor at the boundary. This is going to continue to be an issue for foundation models. They will be very good at the past and not so good at the boundary. Is that a problem? Yes. Can you correct it? Yes. Prediction-powered inference and simpler methods could do that. In my remaining 1 minute, I want to mention the other issue about bias that arises more in an economic sense. There are incentives at play when data flows. So clinical trials cost tens of millions of dollars per year. The right way to think about this is it's not simply a statistician analyzing data and deciding what medications go to market. It's a principal-agent situation. The principal is the regulator. The agent is the pharmaceutical company. The agent is supplying proposed medications, proteins, and the agent knows something about that the principal does not know. The principal has to do a blind test. So the bias is coming from the particular hypotheses that are sent to the principal, to the regulator. And if you ask how a regulator should test, a statistician will tell you to follow the table at the top. You see that the type 1 error, the false positive rate and the false negative rate are very low. That's very good. But if you put this in an actual real-world situation, you have incentives. If there's not much money to be made from this particular protein, even if your drug is not very good, you're not going to send it in. But if there's a lot of money to be made, if your drug is not very good, you will send it in and hope for a false positive. Those are the incentives at play that leads to lots of medications going to the market that are not actually effective. So again, this is a problem that can be solved. We have developed a new technology called statistical contract theory, which takes the idea from economics of a contract, a set of options like business class, economy class at different fares, and then turns that into a data analysis setting where you get different kinds of reward depending on the outcome of an experiment after you make your choice. Okay, so this is algorithmic design that blends data analysis and microeconomics. And if you want to think about what this is in the context of the word AI, to me, AI is the overall technology of our era of how to design systems. It's a problem-solving enterprise. It's not a technology. It's not ChatGPT or AlphaFold. It's the problem-solving mentality that went into the design of those systems. And we're only partway there. We're very much getting started. Thank you.
Thank you. Last but not least, we are going to hear from Whitefield Diffie, 2015 Turing Award winner. Please.
I wrote a keynote on a rather broader subject, and then I discovered we had a topic. so I wrote one on our topic. Now you're stuck with that. My name's Whitfield Diffie. I am here because of work I did 50 years ago in cryptography that's had a big effect on the way the internet works. But I don't exactly understand why, it qualifies me to answer anything about whether AI is renaissance or doom. I have two plausible answers to that. One is that if you know anything, they think you know everything. Haven't figured out whether that's true or not. But the other is that although only one piece of my work would I regard as at all in artificial intelligence, I grew up in the artificial intelligence community. I knew Minsky, McCarthy, Putnam, Letvin, Selfridge, all quite well. And I was acquainted with all the rest of them, Claude Shannon, Norbert Wiener, Noam Chomsky, etc. So, maybe if I didn't eat enough of it, I took some in through my skin. So my answer to the question is, of course, both. AIs are already tremendously useful. Given what's being invested in them, unless there's some amazing error that doesn't show, we are going to find them much more useful in each succeeding year. But people are worried, will AIs take over the world? And I think the answer is just unquestionably, of course, right? Because people like having things done for them. And the AIs are incredibly obliging. And you ask them to do things, and they do them. And yes, at present, a significant number of them are detectably wrong, so you get irritated with the AIs, try a different one, wait 6 months, whatever. But the basic mechanism is, if this gets better at its present rate, you're going to get what you want out of it. Well, that means that somewhere, probably prior to 2050, AI is going to be doing everything, 97%, 98%, I don't know. But you'll suddenly find that trying to throw them out is like trying to throw the government out. Right? They're doing this huge range of things that you need, and so you are stuck with them. So I don't think there's any fight with the AIs or anything like that. I think we're just going to adopt them until we discover there isn't any alternative. Now, there's one area I have a non-standard opinion in. People talk about guardrails in AIs and having AIs, not tell you how to murder your sister-in-law who was so offensive at dinner last night. I think that is a very bad mistake. Because when you create a class that has the authority to tell you what it's willing to do for you, you can't. That's a keep the small people in their places mechanism, but it is not their authority to say no to humans is not going to end up limited to that. It's not going to be like having an army or police who have great authority and end up pushing people around. Now, something I think would be a great, start would be to adopt Asimov's second law of robotics. This comes from the 1930s, when the first round of science fiction about robots had them all be very dangerous, and Asimov came up with a world in which robots are designed with rules about how you design robots. And the second one is they have to do what people tell them unless it violates the first rule, which is they can't hurt a person. I mean, that would all be very nice except as far as I can see, we're not vaguely going in that direction. We're now arguing about whether autonomous drones, why is ours sitting there on the bottom? Should be allowed to kill people without referring to higher authority. And so I think I don't see any sign of the control of AI being on the way. Thank you.
Thank you very much. We are now moving to a panel that has two people in it. One of them is Stuart Haber, who I just learned, by the way, is one of the co-inventors of blockchain. So he's with us. And in addition, we also have with us Dr. Kai-Chen Dong. Together, they'll try to answer some of the questions, simple questions that I composed for them, and I may add perhaps a bit of my own, and possibly we'll hear from you after that. So here's the first question for the panelists. As we just heard, AI has a very clear potential benefits for society, but at the same time poses serious potential challenges. Can you identify, if possible, the single most important benefit and the single most important serious challenge that AI poses? Please, Stuart, can we start with you?
Okay, may I? Okay. Good morning, distinguished colleagues in science and also our guests. So I'm Kai-Chen Dong. I'm a young faculty member of Tsinghua University. So I would like to answer this question based on my personal experience with young scholars, young graduate students in my group. Well, to me, the best thing about AI is about in education. I still remember the day when I was a young PhD student. I was asked to learn the roadmap of one single technology in order to get prepared to do innovative research. And I spent days, even months, reading hundreds of papers, just try to understand everything, tracing date back to 18th century all the way to the papers published yesterday. Well, it was painful and time-consuming. But now we see large language models. They may help us collect papers and generate a short report including all the key notes of the papers. And my students, well, they are able to grasp new knowledge in a short period, much faster than me years ago. So I think it accelerates the speed of education so that we do not need to spend lots of time in learning something old. And I would like also to mention something about research. I totally agree with Professor Levitt about the speed of the research we do today. Well, when I was in UC Berkeley, our pulse laser deposition tool is far away from material characterization tool, so I need to walk up the hills and then do pulse laser deposition for hours to get thin films done, and then work down hills to do the characterization. Well, I can only do 3 thin films like in one day. So, but now we are trying to speed it up. I want my students to avoid from suffering what I suffered before, so we are trying to connect robots with the thin film deposition tool so that students can sit in the office while monitoring what is going on in the lab, and also AI agent may also be able to help increase the quality of the thin films. So to me, the best thing about AI is it accelerates almost everything in education and research. The challenge, on the other hand, may be the students, well, they trust AI too much. Well, I found one mistake from my student. I asked, oh, why you made that mistake? He told me, oh, it's by the AI. They told me this value should be this number. But AI has some illusions, right? But students, they are young. They may not understand that. They just be too lazy to try to think about it themselves. So I'm just concerned about that. In the future, maybe students may rely on AI too much. Are they tools of AI or AI tools of them? I don't know. And I heard about some conferences are trying to introduce AI in evaluating submissions, like during the peer review process. So maybe in the future, can AI really evaluate our innovative submissions and our new work based on the previous knowledge? I have no idea about that, but I think it's a challenge. And to take a step forward, how about AI will evaluate and rate our research proposals for funds? I don't know if it will happen or not, but I'm just concerned about AI will determine the future scientific development of the society. It may not happen, it may happen. I have no idea for now, so that is the challenge to me. Thank you very much.
Thank you. Thank you very much. Stuart, please, your thoughts?
Okay, first, I'll say a couple of words of introduction. I'm Stuart Haber, and I'm in a position a bit like Whit Diffie a few minutes ago. I'm here at this event for some work I did a while ago, not quite as long ago as Whit's work, but not so recently, in the field of cryptography, which may or may not prepare me to say anything particularly intelligent about AI, but I'll try a few words. The biggest benefit, as indeed we've heard from several different points of view, is improved science and technology. The AI helps all of us as scientists and engineers to do our work, and it's hard to predict what this may do decades hence, but we've already heard about a bunch of examples in medicine, and I look forward to seeing what happens. The biggest challenge is, again, of course, improvements in science and technology, which can be used for all sorts of nasty purposes. But a particular challenge that progress in AI worries me is the great proliferation of deep fakes, scams, poisoning our social environment, and our shared notion of truth. A poisoning that it is so bad that much of the world no longer shares our desire for truth that underlies most of the science, well, all of the science done by people in this room. We can't even, as a population, agree on which way is up. That's worrisome.
Well, thank you very much, Stuart. You said that you may not be qualified. I'm thinking about myself, qualified, and I shatter. So we'll move anyways with this, and we'll move to the next question, which is, given the impact of AI, is there a need for global regulations in order to harness the AI revolution and contain its potential damage or challenges to society? If so, can you suggest what might be this type of regulation? I may add, we all know that AI is changing so fast that we don't actually even know what's the nature of AI in a few years from now. So to suggest regulations for that is difficult. But this is why you are here, to try to do it anyway. So please do.
Thank you for this insightful question, and also really tough. Well, so well, I think scientists are kind of romantic. We like uncertainties. Well, uncertainty will born new inventions. So I used to read some science fictions about the wasteland or cyberpunk, and I'm just too concerned about that future to come in, right, in like 100 years. So my answer, I'm not this field of expertise, but yeah, my answer should be yes. We should set some right lines based on some common agreements. But since different countries and different regions may have different situations, so the details may vary from case by case. So that's my answer. Thank you.
Thank you. Stuart, please.
So I would agree that there definitely is a need for global cooperation in regulating AI. This should be an international effort. Unfortunately, these days, international cooperation is not the it's in trouble. I don't have anything to offer on that, but fortunately, there is something that technology can provide, namely the use of cryptographic tools to provide proofs of provenance. This is to face the problem I mentioned earlier of our deepfakes, scams, notions of truth. The blockchain, as I can speak from firsthand experience, was invented not to create money, but to provide proofs of integrity for digital records, to enable users of digital records to verify that they have not been changed since they were created or registered. I did this work with my fellow inventor, who's here in the audience, Scott Stornetta, and he and I have a new project that we call SureMark, which is meant to fight deepfakes by adding a layer of verifiable, unforgeable social identity on top of the current internet. I will not describe this in great detail now, but that is a use of technical tools. In fact, the main technical tool is due to Whit Diffie, and his co-authors, digital signatures, to establish provenance for digital records.
Thank you very much. This, by the way, this question is really difficult, not just because we don't know what shape AI will take in the near future and in the longer term future, but it's also because it's a long process. It reminds us maybe that when there are major revolutions, it may take decades to take care of some of its ramifications. The Industrial Revolution, it takes the humanity decades to try to overcome some of its problems, and I'm sure that the same thing will happen here. It shouldn't stop us from trying already now to do that. And as maybe Stuart said, perhaps the single most important thing that we need to keep is checking, just making sure that facts are facts and not the way the world is looking on right now. It's a challenge that I hope we'll be able to overcome. I'm going now to move to a strange topic, because we most of the time talk about the function of AI, its goals, its problems with the goals. But AI already has an emotional aspect to it. Michael Levitt just mentioned that it moved from being helper to assistant to being a colleague, and who knows what's going to be in the future. Now, with that respect, it might also have emotional aspects to it as well, and I'm going to ask you to speculate about that. And here's the question. Can you speculate about the impact of AI on social life? Will there be relationships between AI-based entities and humans? And if so, is it good, bad, neutral? And lastly, but it's important too, will it affect social relationships between humans? The fact that we have also relationships with AIs or AI-like robots. Please.
Thank you. Another difficult question. Well, let me give one example here. Let's see. When I express my opinions, so some people who agree with me may like me, while others may dislike me due to my expressions. So what if I say my previous two answers were generated by large language models? Of course not. I'm just giving one hypothetical example. So if I did that and the people judged my opinions based on my answers generated by AI, so this is, I think, is a good example that AI does affect my social life. Because I use answers from AI and people judge me based on my answer, they don't know if I use AI or not. So in the future, as I observed, the younger generations, they grew up with AI helpers, with luxury models installed in their cell phones. So they naturally, I guess, they will naturally trust AI answers in making decisions. And in that way, I think their social relationships will be largely, at least affected by AI. Well, is it good or bad? It's hard to say. But considering that we have been through so many challenges in the past thousands of years, and we have seen many technological revolutions, and we always finally come up with a way to make use of them to help the development of our society. So I'm really optimistic about the future, and we can make good use of AI, and we can get better in the future worldwide. Thank you.
Thank you. Stuart, please.
So it's hard to speculate on this question. I don't have too much to say about social, about interacting with technological entities as social beings. Maybe that is because I'm too much of an old fogey and I haven't played with them like the younger generation. Will it change? I do not expect AI to change human nature. It will give us new tools to do new sorts of things, but I don't think will change human nature in essential ways. But we'll see.
Well, I'll just add to it, as someone that dealt with memory, among other things, people's use of memory changed over time. Nowadays, we don't have to remember phone numbers. We don't have to do a lot of things. Some of the facts, we just have to look. If AI doesn't interrupt, we have to look and see elsewhere for the facts. But it hasn't really, as far as we know, changed the structure of the brain or the structure of the brain memory capabilities. It does affect behavior. And I wonder if, in that respect, not in terms of changing our nature, but in changing our social behavior, would it happen?
It's, well, the fact that we are here in this room is something we could only do with, as a result of some centuries of technological development. The AI is another set of tools that will, if we don't blow up the whole planet, will bring new things.
I guess I'm going to leave at least one option from the people that listen. If anyone wants to say something, then we'll have one such comment. Anyone?
Yeah.
Please.
A number of people, I should say, this is Bill Phillips, I'm an atomic physicist. A number of people have mentioned that AI can be very useful in allowing a lot of research in a short amount of time, but that one needs to be careful, that the students in particular need to be careful they don't trust the AI too much, which means that you have to do some of your own research to make sure that what the AI said is consistent with reliable information. Now, I would imagine that all of you think that the balance between saving a lot of time on the initial research and having to spend some additional time verifying that the AI isn't hallucinating is still on the positive side, that it's still better to start with the AI. But what I'm wondering is, do you think that when you've achieved that advantage, that you have as much confidence about the reliability of the research compared to if you'd done it yourself?
Well, maybe it's a good question to have with us. You know, as scientists, we always believe that eventually converging evidence from different aspects will help us decide. That's how we always did it, and that's how I hope we'll do it with AI as well. So I'm going to conclude this panel. I'll just remind all of you that at 1 o'clock we convene again to a question that is related but perhaps even more functional. Can AI discover anything? We'll hear about it at 1. Thank you all very much.
Ladies and gentlemen, we will resume our sessions in this hall after the break. It's about to begin. Ladies and gentlemen, distinguished guests, we are about to begin with the World Laureates Summit AI Science Forum. Can AI discover anything? Please welcome Professor Tony Fan Chong Chan, former president of King Abdullah University of Science and Technology.
Good afternoon. Welcome to the postponed morning session. Now it starts at right now, 1 p.m. So the format is this. I was just informed, okay? So I'll give some opening remarks. Then we have 5 keynote speakers. Each one allow absolutely upper maximum is 6 minutes. I don't care whether you are laureates or not. I'll cut you off at 6 minutes. Then we have a panel. So the 3 panelists, we each get maximum of 3 minutes to speak on the topics. Then we have a panel discussion that involves all the speakers, the 5 keynote plus the 3 panelists. I think that's the way. Hopefully we have time for that. Okay. First of all, it's a great honor to be asked to chair this session. When I look at the program, it turns out I actually know 4 or 5 of the panelists. I did not put together the program. The theme is called, Can AI Discover Anything? I mean, that's a pretty aggressive title. I know if somebody working on AI, they should feel they should stand up and answer that question. In a way, I feel there's no better forum than this one to address this issue, because obviously there are many Nobel laureates in the basic sciences, and there are also many Turing Award winners who sort of represent computer science, and some of them are AI. On a personal level, I used to work when I was active in research in computer vision, and nobody calls it now, it's all AI. And also, in addition, I was the assistant director of math and physical sciences at NSF, the US NSF. So that gave me a little peek into how physical science work, and I myself is AI, so I sort of have a foot in sort of both sides. So to answer the theme, can AI discover anything? My personal answer is yes, but, okay? Why yes? Factual point. Recent years, there were 2 Nobel prizes given to AI, as you know. Was it 2 years ago? There was one in chemistry, and AlphaFold, the other one in physics. Okay, so obviously the Nobel Committee think they have made enough of a contribution in science to warrant awarding their prize. But no, at least not to the extent of replacing what many paradigm-shifting scientists discover, like some of you here. I hope you agree with that, okay? The current approach to AI, as many of you know, is based on huge data, learning using neural networks, and huge compute, NVIDIA, GPUs, and so on. The question is, can this approach discover all that is to be discovered in science? So that's for the panels and the panelists and so on to answer. So I want to say, I want to keep on referring to Einstein, because that was referred to before, right? So Einstein, it doesn't work, this one? Okay. Hello, is it better? Okay. Einstein used thought experiment. So some people will say he did not use big data, okay? So here's my thought experiment for all of you to consider. If someone else besides Einstein had the best AI model pre-1905, would that person be able to discover general theory of relativity, okay? Or quantum mechanics, not been invented yet. Because these data were not in the data. Somebody was saying, even for current data, they're very good. For future data, they're less accurate. Well, it's not accuracy. They've not been invented. So then what happens? A lot of talk about artificial general intelligence, AGI, or artificial superintelligence. There's no definition. But whatever the definition is, I think it should include the ability to create paradigm-shifting science that Einstein, Maxwell, Darwin, and so on, Crick and Watson, they have done, including many of the work that people sitting here have done. Okay. So last point I want to make is the organizer asked me to send sort of 4 points for panelists to consider. So I just summarize it and remind everybody. First one is, what's your view on whether current AI approach can achieve AGI or SI? If you believe so, when? Okay. Second is, even when AGI has been achieved, will we still need scientists such as Einstein and so on? What would be the role of ordinary scientists, not people sitting here, that we are nurturing today? Okay. Would they be just in discovering, what would be the role of AI in advancing science? Would it be discovering connections in this data? Would it be in optimizing or augmenting current science processes? Can AI discover paradigm-shifting new science? Are there fundamental limits to what the current approach to AI can discover in science? Are there any limits? Okay. The last point is, what should we, as a group, many of us are with university, how should we nurture next generation talents in AI? What are the distinguishing roles for academia and industry? Industry has a lot more resources, both in terms of financial resources and computing resources than university. So what should we do? So those are the 4 points. So let me turn to the first keynote speaker, and that's Professor Jack Dongarra. He is the 2021 Turing Award winner. He is known for many things. I think, limited time, I give all the time to you without reading all your contribution. It's online anyway. But I do want to give a personal note. So Jack and I have known each other professionally for over 4 decades. And he's well known in the field, so I can attest to his contribution personally. But he's well known in our field to have his work on the license plate of his car. You can ask him later. Jack. Yeah, please. 6 minutes.
Right. Well, thank you, Tony, for that introduction. So I'm going to talk about high-performance computing. My area of research is in developing algorithms and software that run on the fastest computers. And I'd like to begin by taking a look at science and how things are done. So traditionally, scientific and engineering has relied on theory and experimentation. So theory is a paper and pencil process where we go and try to look at new ideas. We think about that didn't work quite as well as predicted. And we think about experiments as testing the theory. We build something. We may, in fact, go back and change the theory based on the experiments. There's an interplay that takes place between that. And today we're using computational science as a third, I'll call it pillar, to supplement the ideas used in theory and physical experiments. So we use high-performance computers to simulate physical phenomena that are based on these physical laws and numerical methods. And we look at high-performance computers to help us with that process. So we can think of these high-performance computers as sophisticated scientific instruments, sort of like the Webb telescope, but only for a much more general set of topics. So computational science fits into that. And HPC really involves aggregating the computer power that we have today to solve these complex problems with high-speed computers. And given that we have tremendous advances that happen as a result of using these machines. We use them for clean energy, for looking at the power grid and improving it, for climate change, for cancer research, looking at advanced materials, and also for catalysis. So those are just some of the ways in which we use it. And we've seen this incredible change take place in our computing devices. You know, we have, when I started computing about 50 years ago, the computer that I was using was a Cray computer. Cray is based on vectors, vector instructions. That's how it got a lot of its performance. And after that came parallel computers and distributed systems. And after that came the rise of GPUs, or graphical processing units, which we use really to extract and to boost the performance of the floating point operations. And it turns into clouds and high-performance computing. So we've seen this transition from vector to shared memory parallel computers to distributed to massively parallel to clusters. And today we have this accelerated computing, which uses GPUs and conventional computers. And on the horizon, of course, is the potential for doing quantum computing. And AI is really augmenting all of that computation to help us understand things better. I've been involved in algorithms and software, and those algorithms and software have really followed that trend, that technology that's been improving, trying to design software that runs effectively on those machines. The one thing I will point out is that the evolving software and algorithms always follow the hardware developments that take place. So there's a lag in time before we can actually use the machines at their potential, and that's because of having to rework the algorithms and redefine the software that runs on those machines. This is a plot of the fastest computer over the past 36 years. Today, the fastest computer is a machine at Lawrence Livermore National Lab. It runs at 1.8 exaflops, so that's 1.8 times 10 to the 18 floating point operations per second. So a floating point operation is 64 bits in this context. So 16 decimal digit adds or multiplies. So 1.8 exaflops. I have a hard time getting my hands around that number. So an exaflop, that's the number of seconds since the Big Bang is measured by 10 to the 18 seconds. So that's sort of the magnitude that we have here of this number. And back in 1993, the fastest computer was a machine at Los Alamos National Lab, and it ran this benchmark at about 140 gigaflops. And today my laptop can outpace that machine that was used back in that time. So incredible changes over a very short period of time. So HPC is really synonymous with numerical modeling and generative AI. The deductive world of physics-based mathematical models is increasingly being augmented today with the inductive world of surrogate models that are created by generative AI. These hybrid models are rapidly expanding in a rich parameter set of spaces and taking the modeling much further. So weather modeling is a good example of that. So traditionally, weather modeling has been done by numerical models. Today, with the analysis of 40 years of data, the AI can really be in a position to predict the 10-day forecast in seconds rather than in hours for the numerical methods, and do it in a way that's actually much more accurate than those numerical models. As an example, the ECMWF, the European Center, is switching over to use AI to help with its productive things. And as Tony mentioned, protein folding through AlphaFold and Rosetta Fold really have increased the accurate prediction of these 3D structures, and that gave way to a Nobel Prize a couple of years ago.
Thank you, Jack. Time's out.
Time's out. Okay. So many other things can be done with AI, and I just want to point out that Today, we have this constantly changing world from scalar to vector to distributed to accelerated computing with using mixed precision today. Again, hardware advances quickly. Algorithms and software follow those advances. And I think I'll have to end there because Tony's about to cut me off.
Thank you very much. Okay. So next speaker is Bob Tarjan. I looked up a citation for his 1986 Turing Award. It says 4 fundamental achievements in the design and analysis of algorithms and data structures. His work, recognized for its profound impact on computer science, includes developing efficient algorithms for graph problems and pioneering data structure. So that's the full quote. Just a personal note. I was in his class at Stanford. I just reminded him when I was a graduate student. And I follow his footsteps from Caltech to Stanford in the same field, in the same department. So Bob, please.
Thank you. It's a great pleasure to be here and an honor. AI systems, as we know them, hallucinate. I have some personal experience of this. I attended a similar meeting, and in preparation, the organizers prepared a CV for me, which gave me 2 awards that I never received. I asked them about it. ChatGPT prepared the CV. So these systems hallucinate. This is important to think about. I'll come back to that in a minute. My field of research is design and analysis of data structures and graph algorithms. It's some plumbing layer in computation. Let me begin with a few observations about computer science. Unlike physics and mathematics, computer science is a very young field. The work that I do in algorithms and data structures started more or less in World War II, or you can give examples before that. So that's 60 years during which we've developed beautiful, theoretically efficient algorithms and data structures, but computer science is still a young field. We've often settled for the first good enough solution, but it may not be the best. The design space is rich, and as computers get faster and memories get bigger, the design space only gets larger, and we need to explore the enlarged design space. So my objective in research is to develop and analyze what I'll call reference algorithms. It's really mathematics. Paul Erdős, who was a well-known mathematician, had this idea of proofs from the book. This is the book in the sky. We can think of algorithms in the same way. We want to develop algorithms that are as simple as possible with provable resource bounds that are efficient in practice. Einstein supposedly said, make everything as simple as possible, but not simpler. So that is the goal here. So let me just mention some examples of problems I worked on having to do with graphs, which are points and line segments connecting the points. So a simple question is, can we embed a graph in the plane so that no 2 edges cross? This is the planarity problem. This is important in circuit layout because if you have connections in the circuit that overlap, you're going to get short circuits. Together with John Hopcroft, who was my co-winner of the Turing Award, we came up with a linear time algorithm for testing planarity based upon depth-first search and some data structures. Another example, specifically to data structures, was an analysis of a very simple algorithm that allows you to keep track of connected components in graphs. Think of the Facebook friendship graph. Are 2 people connected by a path of friends? And what happens when we add new friendship relations? How do we keep track of the connected components on a graph of billions and billions of vertices? We want to have a data structure that allows us to add edges rapidly and update the graph. So there's a beautiful and simple algorithm for doing this, which seems to run in constant time per operation, but it turns out not. This algorithm is simple, the analysis is complicated, and the analysis gives a solution that's the inverse of Ackermann's function, which I won't describe, but is a function invented by logicians for a completely different purpose, and it grows incredibly rapidly. It grows so rapidly that the inverse function cannot be, you can't tell the difference between constant and this very slowly growing function by any kind of experiment. The most recent project I've been involved in is shortest path algorithms. You have experience with this with your favorite mapping application. You can compute the exact shortest path distance on a road network almost instantaneously on your cell phone. There's a lot of technology and algorithm design behind this, and recently we were able to prove that in a certain sense the fundamental algorithm in this area, Dijkstra's algorithm, is best possible in a very strong sense. What kind of tools are involved in this research? Finite mathematical tools, combinatorics, mathematical induction, logic, finite probability. Lots of interesting questions. What I tell my students, and what is really true, is asking the right question is more important than finding the answer. To be a really great researcher, you have to develop a certain kind of taste to identify those problems that are really crucial. Now, what is the role of AI here? It can't hallucinate. The kind of things that AI could help me in my research do are, first of all, provide rigor, fill in proof details, find missing cases, build counterexamples. Explore the proof space. I have a conjecture. Can the system prove this for me? Explore the design space. Can an AI invent new algorithms for certain kinds of problems? Going beyond this to more general questions.
30 seconds.
I'm almost done.
Okay, thank you.
Can AI explore the problems space? The whole same question you were asking. Can it come up with general relativity or quantum mechanics on its own? And I think all these questions are still open. Large language models are not the kind of AI tools that are needed to address these particular sorts of questions, but there are certainly mathematicians who are actively working to try to use AI tools to solve some of these problems. Thank you.
Thank you very much. Next speaker is Ariel Washoe. His 2013 Nobel Prize citation reads like this: for the development of multi-scale models for complex chemical systems. Now, in a way, this is close to what Jack talked about, scientific computing, but using on chemical and biological system. I've always known about his work, so please, Ariel, where you are.
Okay. Thank you very much. And I will talk on the relationship between physically based simulation to AI. I will give several examples. My first example. What? It's called a maximum entropy. So how do I go back? Okay, my first example is trying to study enzyme design by massive use of computer simulation, where we have a lot of experience. We took the enzyme Kemp eliminase, which was refined by directed evolution, and we tried to see if we could reproduce the result of directed evolution in terms of the catalytic efficiency. The blue are the fastest enzymes, and after a lot of effort, which continued for many years, we found that we are in the range of the predicted directed evolution, of the observed directed evolution, but we are not good enough. And since I work in this field for like 40 years, I decided to try something else and move in desperation to AI. We use maximum entropy to try to see if it has any correlation with catalytic efficiency. And for several enzymes, we found very impressive correlation. I'm not sure if, where the energy of maximum entropy is directly correlated with the catalytic power of different type of enzymes. And the catalytic power was not included in the learning process. So regardless of the reason why it worked, we were able to predict, at least in one case, naturally evolved enzyme which is faster in one step than what evolution did. So it's clearly some accomplishment of AI. We then tried on bioluminescence, where the enzymes in these creatures try to get to the most blue direction because the creatures live in water and you want to pass the visible range in water. And again, with maximum entropy, we found a very nice correlation which allow us, this is not the correct slide, but anyhow, which allow us to even suggest improving luciferase, which have large industrial application. Now, the most recent example, or almost the most recent, is associated apparently they did not change the slides, which is not nice. Okay, we took kinesin, which is supposed to be here in the movie. Its walk in one direction, and one of the puzzle is what makes kinesin and other myosins walk only in one direction. We spent a lot of time trying to figure it out, and we discover that it's not due to any magic idea like power stroke, but actually to the rate determined step and the barrier for this step. And we studied it with many systems, but maybe the most impressive one, which is very recent, it was just published, was a kinesin-like system which has very strange feature. In some mutation, it's go forward, and in other mutation, it stop, and in other mutation, it goes backward. So first, we studied this system by physical-based simulation. We study the ADP release rate-limiting step, and we look for the barrier, as you see. In some case, the barrier for the mutant is higher. In other step, it's lower. And in the last step, it just stops. So by physical simulation, we were able to understand why this is happening. And then we just play a little with AI, with maximum entropy, and we found that there is a nice correlation, not really good enough, but there is a nice correlation between the maximum entropy prediction to the directionality. In this case, we were overexcited, and we tried to apply this to kinesin, which are involved in heart disease, where we were very successful with physical method to get the right directionality, but maximum entropy did not do too well.
Time's out.
Since I have, okay, so anyhow, this is not the end of the story, but several examples. Thank you very much.
Thank you. The next keynote speaker is Yuri Nestorov. He is the winner of the World Laureates Association Prize in Computer Science in 2023. He is an expert in optimization algorithms. He won that prize together with Nemirovsky. So the citation says, their work has sparked a revolution in the field, leading to the development of new algorithms that are more efficient and scalable. And I suspect these algorithms are used a lot in deep learning problems in the world. So please, yeah.
Okay, thank you very much for this opportunity to discuss artificial intelligence in this audience, but it seems everybody in this room understands this differently. Therefore, let me start maybe with general remarks. As you know, that in the last decades in the computer science, we observed a sequence of revolutions, like invention of personal computers, development of internet, and availability of big data models. Finally, we have seen maybe the most important event in the history of sciences, the birth of artificial intelligence. Its appearance was widely recognized in view of the remarkable success of neural networks. It was achieved by creating a system of sciences responsible for different facets of human activity. Note that the main tool for generating the new knowledge in all these sciences, maybe except math, is the verbal convincing reasoning. For artificial intelligence, this doesn't work. It accepts only the results of computation represented by numbers. Hence, we need to create a system of new sciences suitable for the needs of artificial intelligence. This is an extremely challenging task, and now we're only in the beginning of the process. We only start learning how this can be done efficiently. By analogy with human intelligence, it is clear that we need to create at least two things. The first one is the virtual reality, which is the main object of investigation of artificial intelligence. This reality should exist in the form of big databases accumulated in the powerful data centers. Creation of this part of the system is very expensive and time-consuming. Hence, comparison between different actors of this field is very reasonable. Note for the human intelligence, we get the surrounding reality, so-called the world of things, for free. The second element in this system is the artificial intelligence itself, the unit which must be able to generate specific answers or decisions requested by a human being. Its performance is achieved by a training process provided by the available database. At this phase, machine learning should be already involved, since it can endow us with an efficient training procedures. In principle, the education process shouldn't be too expensive. If we compute the total energy spent for development of intelligence of a human being, say for the period of 20 years, we get an upper estimate in 17 megawatt hours. In the current prices for electricity in Europe, this is less than 5,000 euros. But of course, the training algorithm for a human being and for artificial intelligence are totally different. The nature had millions of years for selecting the best procedure by the straightforward natural selections. For artificial intelligence, during the last decade, we just started verification of different strategies. Most of them are based on optimization models and employ the numerical optimization methods. However, we still lose several orders of magnitude in the guarantees for the required computational time. We hope that this is a temporary inefficiency, which will be eliminated by the further development of the field. This is the situation in machine learning right now. Coming back to the main topic of our discussion, I believe that artificial intelligence has indeed a considerable creative power. It can discover new links, structures, and properties of the investigated objects. But there is an essential difference with the conclusions of human intelligence. When a biologist investigates a certain object, say bird, the conclusions will be related to the real bird. However, the conclusion of artificial intelligence can be related only to a model of the bird which exists in the corresponding virtual reality. If the model is done correctly, then this conclusion can be used in the real life. If not, it could be a complete nonsense. To conclude, I would like to repeat that at this moment of development of artificial intelligence, it is highly desirable to establish cooperation of different partners for creating a detailed virtual model of the reality. This model can be used later for training different artificial experts, which will be educated for working in different domains. The creation of such experts should be relatively cheap. It can be done by different firms using the common database treated as a virtual reality model. Thank you.
Thank you very much. Thank you for finishing ahead of time. Thank you. Next speaker is Professor Omar Yagi. He is the 2025 Nobel laureate in chemistry. His citation reads very simply for his pioneering development of metal organic frameworks, MOFs. It reads like science fiction. It can be used to capture carbon and water from the air. I should add one personal note. He's now at the University of California, Berkeley. So I hope you agree. I was partially responsible for recruiting him to UCLA, but I'm not responsible for losing him to Berkeley. Thank you, Omar.
Thank you, Tony. Let me start by saying that making new chemical structures and new molecules is at the heart of science. And one of the biggest difficulties in making them is to make them in an ordered form, meaning to make them as crystals. So while sometimes, as we have done with MOFs, COFs, and other materials, it's easy now to make MOFs and COFs, but it's not so easy to crystallize them. It takes a student potentially a year to 2 years, maybe sometimes in the case of COFs, 3 years to make crystals of these materials. The reason crystals are important is because we want to characterize them on the atomic and molecular level using single crystal X-ray diffraction. And we also, in some applications, crystallinity or the order of the material is extremely important to its function, such as in the case of water harvesting from air. So let me just say that the interest in these materials lies in their ability to encompass tremendous amount of space, that in 1 gram of one of these structures, like maybe the size of a sugar cube, encompasses as much space as an entire football field. And recently, we've been able to even make them encompass space that is double a football field for each gram. So this exciting property makes them extremely important. Various applications, in fact, hundreds of applications are being pursued right now in the community, and some of them dealing with water harvesting from air. This is where the structures are programmed to pluck out water from air and make concentrating the water into the pores. This is now becoming almost a commercialized product. It will be unveiled this year, a product that would produce almost 1,000 liters of water per day, every day, for 6 to 7 years, with no energy input aside from ambient sunlight. So we've solved, let's say, the water harvesting problem. Now we can create water from thin air, and we can take CO2 out of the air. Why am I telling you this? Is because it has taken us 35 years to get here. And that's what makes AI so exciting to me. And so I'm going to give you 2 examples of how we've been using AI very effectively to accelerate not just discovery, but also the development of the devices that ultimately are commercialized. I call this field ametry, AI mixed with materials and mixed with chemistry. And ametry is about deploying AI tools to make them productively useful in chemistry and in making materials. I'll give you a simple example. This is for the young people in the audience. This is familiar. For people like me, it's not so familiar. This is a long prompt given to ChatGPT. And basically, you're telling ChatGPT exactly what you're doing. You're saying you are a reticular chemist. That's like my brand of chemist, developing a particular cough. You have a robotic platform that will execute the experiment. Your taxes, conduct literature, whatever. You're giving it all the instructions, including actually creating a reference list and making sure that it does things accurately. And the idea here is that we wanted ChatGPT to give us the conditions under which to crystallize a specific cough that has been really difficult to crystallize. For 10 years, the whole community has been trying to crystallize this. And so it spit out a whole bunch of conditions that we ultimately put in a robot and put in the results of that data. So here's the experimental cycle. We take the conditions generated by ChatGPT, we do the experiment in the robot, solid dispensing, we do all these different things, and then we characterize by high throughput powder diffraction and put these results back into ChatGPT, okay? And so we did this cycle 3 times, and we were able to get not just one well that has high crystallinity, but we were able to make that crystallinity 3 times what the community has been trying to do for the last 10 years. So 3 times as crystalline. This is truly revolutionary for the way we're doing chemistry today. And so it has changed my entire group from just an experimental group into a group that blends AI with AI tools and LLMs. The other thing is that we've designed, right now, we are following these 3 cycles. One is a predictive cycle married to an experimental cycle, a synthesis cycle, and then the other one is a scaling cycle, which has to do with the application. And these 3 cycles work together. One feeds into the other. And the more frequently you go around these cycles, the better these machine learning models get. So when you adapt your machine learning algorithms to this kind of chemistry, what the students that are using these cycles can do is double the rate of discovery compared to students that are not using these machine learning algorithms. And so yes, we can make not just new compounds, but new compounds that experts in the field would not have anticipated. So can AI help us in speeding up discovery? Yes. Can it simplify the tasks and eliminate a lot of the trial and error that we chemists use to crystallize things? Yes. Will it get better? Yes. The more we use it, the better it will get. And I think we are in the middle of a revolution transforming chemistry by blending it with AI.
Thank you.
Thank you.
So help me out. So the panelists and I will go to the stage for this part. Right, there are seats up there. So the 3 panelists, I don't know where you are, please.
Put these results back into ChatGPT, okay? And so we did this cycle 3 times, and we were able to get not just one well that has high crystallinity, but we were able to make that crystallinity 3 times what the community has been trying to do for the last 10 years. So 3 times as crystalline. This is truly revolutionary for the way we're doing chemistry today. And so it has changed my entire group from just an experimental group into a group that blends AI with AI tools and LLMs. The other thing is that we've designed, right now, we are following these 3 cycles. One is a predictive cycle married to an experimental cycle, a synthesis cycle, and then the other one is a scaling cycle, which has to do with the application. And these 3 cycles work together. One feeds into the other. And the more frequently you go around these cycles, the better these machine learning models get. So when you adapt your machine learning algorithms to this kind of chemistry, what the students that are using these cycles can do is double the rate of discovery compared to students that are not using these machine learning algorithms. And so yes, we can make not just new compounds, but new compounds that experts in the field would not have anticipated. So can AI help us in speeding up discovery? Yes. Can it simplify the tasks and eliminate a lot of the trial and error that we chemists use to crystallize things? Yes. Will it get better? Yes. The more we use it, the better it will get. And I think we are in the middle of a revolution transforming chemistry by blending it with AI.
Thank you.
Thank you.
So help me out. So the panelists and I will go to the stage for this part. Right, there are seats up there. So the three panelists, I don't know where you are, please. Hello? Is it on? Okay. Okay, so the drill is each one of you will have 3 minutes maximum to give your thoughts, any thought you have, but also I put out the 4 questions that you can address if you can. And then we will open up to the panel discussion, including the 5 keynote speakers who spoke earlier. I have prepared a short introduction for each of you, okay? So if you allow me, okay? So on my left is Professor Jayan Haritsa from the Indian Institute of Science. He's a professor in computer science and automation. He's a fellow of the ACM and IEEE, and all 4 Indian science and engineering academies in India. Please. Okay, so wait, so let me go on to the other one. Amir, right? Amir Kouashady. He's the 2025 European Research Council STG awardee. He's an associate professor at Oxford. Now, for 3 years, 2021 to 2024, he was assistant professor in computer science and math at HKUST. I wasn't president then, but anyway. The last but not least is Hisham Omran. He's the 2023 UNESCO Al-Fursan International Prize for Promotion of Young Scientists. He's associate professor in Ain Shams University, Egypt. But from 2011 to 2015, he was a research assistant at KAUST, where I was president, actually. We actually overlap, I think, yeah. He's in the field of electrical engineering and communication. Okay, so since we have been going this way, maybe I start with you, Jayant. Yeah.
Sure. Good afternoon. We as humans love to simplify things, sometimes too much, to 3-letter words like AGI or ASI or MAGA, right? So what I would like to say is that we need to ask the question in a more nuanced way. That is, in what dimensions can AI help with regard to the progress of science? And the traditional way of looking at science was that it's in the shape of the letter T, where the vertical stem stands for doing depth-based research, and the horizontal line is for having breadth across various fields. And my view is that humans will continue to have the leading role in the STEM part, which is the depth of research, but in the horizontal STEM, that is where AI can really help, because it can bring many fields together. So we need to actually change the letter T to the letter pi, because you have multiple stems and a horizontal line connecting them. So for example, if you want to show that the lowest theta theorem, which is well known in graph theory, had a very close and subtle and unknown connection to what is called as contrastive learning in machine learning, then that could be something that AI could produce, with the original ideas of graph theory or the original ideas of machine learning would still require a human element. And the reason that I'm still saying this is that if you look at the way that the best research has come, it often comes from people who are from outside the field. And that's because they don't have the tunnel vision or the baggage of having looked at a problem for a long time, which means that they come in with completely fresh thinking. They're not in a sense constrained by whatever they have learned in the past. And this is where you have the Achilles heel of AI. It is a victim of its success in the sense that it knows the past only too well. And often, in order to do the future, you need to forget the past. And humans are very good at amnesia, selective amnesia in many cases. And that is where I think that the humans will continue to have a leading role because they have actually forgotten the past. And whereas if you look at machine learning techniques, they're built on looking at the past and understanding from that. It certainly serves a role for connecting disciplines or connecting ideas in computer science across fields or within the same field as well. Like, for example, I work in the area of database management systems. And the programming paradigm there is very different in the sense that unlike the normal procedural programming that you do, where you have a target and you basically write all the steps to reach the target, in database systems, you just specify the ends and let the system figure out the means to achieve it. And what we have shown recently is that there are many worldwide systems which are very popular, like DB2 from IBM or SQL Server from Microsoft and so on. All of them do good optimization. But if you use the LLM to connect them all up, then you find that you have much better optimization because it can take ideas from many different sources. So again, I would say that the humans give you the depth, AI gives you the breadth. And you should use the symbol pi instead of the letter T to describe research.
Thank you. Almost on time. Thank you. Amir. Amir, yeah.
Okay, so I'm probably
You had to put it closer to turn it on.
Okay.
Yeah.
I'm probably the least qualified computer scientist to talk about AI because my research is in logic and verification. I'm actually quite away from this topic. But the question that was quite interesting to me was whether there is a fundamental limit to what AI or generally machine learning algorithms can do. And of course, from the theory of computation, we have some answers to things that no algorithm can do. We know that there are problems that are undecidable. So definitely the AI systems are not going to be solving those problems. But then I was thinking if there are any other limits, and I was thinking about the actual expectation that the general public has of the AI or machine learning systems. I was actually on X, on Twitter, and one of the things that I see very often is that there is a video or a photo and people don't know if it's a deep fake or it's a real photo, and they ask Grok. And usually Grok just obliges them and gives them an answer, but the answer is not really correct. So I've seen examples where if you ask Grok in different languages, is this video fake, is it AI, or is it real, it would give you opposing answers. Now, I was thinking that actually, in some sense, this problem can be a good example of what can be a limit for what AI can do. Because if you think about it, there are two cases. Either at some point, we will have a machine learning algorithm that can detect these deep fakes, or we're never going to get it. If we never get it, then there's something that the AI systems cannot do, and that's detecting deep fakes. But if at some point we get an AI system that detects deep fakes perfectly, then that means that there are some features in real-world videos and some real-world images that the AIs cannot generate. So in that case, again, we found something that AI cannot do, generating that particular real-world photo or video. I just want to end with one observation. If you look at the pamphlet that was given to you with the photos of everyone who's taking part in this conference, you'll actually see that those photos are deep fakes. So all those photos have gone through LLMs, and interestingly, humans cannot really tell the difference. So when I was looking at those photos, all of them looked real to me except my own. And then I asked other people, and it seems that they can also tell the difference in photos that are of themselves or of close collaborators or family members, but not in general. So I would invite you to take a look at that pamphlet as well and see if you can tell the difference.
Thank you. It's interesting about this limit, complexity theory, what is computable or not. Maybe we can pick that up later. Please, Hisham, yeah.
Okay. So we all agree that AI is very powerful. It has changed almost everything in our life now. It is a powerful co-pilot for scientists, but we need to differentiate between normal science and revolutionary science. So you mentioned Maxwell, you mentioned Einstein. So as Professor Omar Yagi just mentioned, AI can solve puzzles in the current paradigm. but it cannot think out of the box because it was trained inside the box. So it is a great co-scientist or co-pilot for scientists for working in the current paradigm, but for discovering new paradigms, new frameworks, AI will not work. And this is a problem. Why? Because the second point I want to mention is that I feel like we are putting all the eggs in one basket. So if you think about this summit, it is all about AI. If you think about the technical conferences nowadays, everybody is talking about AI. If you watch the news, AI is in the news. If you watch the stocks market, we have trillion-dollar companies based on AI. So if it turns out that we are not going to have AGI or ASI in the near future, if it turns out it is still far away, everything may just collapse. The stocks market will collapse, many companies will go bankrupt, the scientists that were trained on using AI for almost everything will not have the capability to shift gears and look for the next out-of-the-box discovery. So this is a problem. We are putting all the eggs in one basket, so we need to think about this. The third point I want to mention is that when we talk about AI and AGI and compare it to the human being and the human brain, we forget that the human brain consumes just 20 watts of power. Okay, so the limitation now in AI, as many people talk about it, is in the electricity. You are melting our grades, okay? So even if we reach AGI 10 or 20 or 50 years from now, how much power is it going to consume? The human brain, a miracle created by God subhanahu wa ta'ala, is consuming just 20 watts of power. So we also need to think about this. So that's all I have. It is powerful, it is scary, but we need to think about putting all the eggs in one basket. We need to think about creating new paradigms out of the box, and we need to think about comparing it to the human brain will be always unfair comparison because of the power consumption.
Thank you. Thank you. So we have about 24 minutes left, I think. We're supposed to open up to a discussion. Maybe we start with 5 plus 3, the 8 speakers. Let's start with that, and hopefully we can extend it. So maybe if I can take the chairman of this session prerogative, I can summarize a little bit what I heard. I can. I heard from Omar, this transformed your labs, right? Obviously, the AI has been an extremely powerful tool. It changed how you conduct your science and probably others. I heard from Hisham that you were a little bit, say, a little skeptical, and then from Amir, you say, well, there's perhaps some fundamental limit, like computability and so on. So that's one issue that I hope somebody can address, in your field. Which group do you fall into? What's your extrapolation to the future? I think maybe that's a good one to start at. But anyway, the floor is open. You can also ask questions to the other speakers and so on. Yeah.
No, I just in a lighter vein wanted to add the point that AI can never succeed because it's too polite. Most good research comes from tough love, and I'm sure all the advisors here with your students, you have had situations where you actually essentially laid down the line to them, and that has actually worked out very well for them because they have changed their way of working or the way of thinking and so on, and that's required. But if you have something that is always polite, it encourages you to be lazy in a way.
You mean the current AI is too polite?
It's too polite.
Okay. So hallucination is polite. It's just wrong, but it's polite. Okay, good. Any... Please, one here. Yeah, that might should work, I hope.
Yes, thank you very much for this. I was just thinking about the degradation of AI, because if AI is using as input fake news, deep fakes, etc., how do you see the future with the degradation of the information that AI is based on, and how will this evolve? It will be not reliable after a certain time.
It's a matter of trust and discovering the truth, so to speak. Anybody, you want to?
So if I may just add something to that, I'm not really worried about the degradation of AI itself, but I'm very much worried about the degradation of the internet as a whole. Because we are now in a situation where it seems like the vast majority of what you see on the internet is AI generated, and a lot of it is not really high quality content either. So would it get to a point where the internet is just unusable for humans because there's just so much AI slop? I don't really know.
Yes, Omar.
Yeah, I mean, I think that there is no doubt that the future challenge that humanity faces is that the search for the facts. What are the facts? I mean, this is what we do in science, and we're not going to change that when we're engaged with AI tools. We are still putting the human in the loop. We're still making databases that are, some of us, that are verifiable through experiments. So the experiment being interwoven with AI tools is absolutely necessary to making sure that we stick to the facts, which is exactly what we do as scientists. That will never change if we want to remain, if we want to sustain the science in the way that is supposed to be productive and useful to society. The other point about a lot of this doubt about the future of AI and all of this business about extrapolating into the future, I just want to caution that we don't extrapolate too much, because we're still learning what to do. We're still at the beginning of this revolution. We just need to make sure that the steps we take are not sloppy, that we're very careful about what we're doing, that it's verifiable. And I want to just remind everybody that science begins with doubt and questions. So this is very healthy. And, but we also, as scientists, we need to be optimistic. A doubt is good because it says why, and optimism is important because it says why not. We need these two things to work together. So I think that those are, you know, some of the remarks that I want to give concerning some of the comments that have been sounded.
Maybe I can add something to follow up on. So I posed the question of, in the era of AI, how should we nurture our next generation? Let's say we're in universities, many of us are associated with. Obviously, it's not just transmission of knowledge, because you can get it so efficiently, right? And actually, in terms of the way you conduct your business, let's say science, it can really help a lot. I mean, Omar, you make a very good case of that. But I think, so in terms of nurturing scientists, it should be judgment, like what you're saying. You know, how do you do the background due diligence? How do you gather the right data, talk to the right people to find out whether something is fake or true? I think maybe that's more important than actually learning how to code, okay, to me. Okay, so that's one view. I was just at a conference that talks about this. You know, so the conference is called AI and Humanities. It was in Washington, D.C. So I can tell you the humanists, many of them are worried to death about that they will be completely replaced by AI. Because everybody will study AI, nobody will care about philosophy and ethics. But my view is that there's no better time no more important time for the humanities than now, because of what you ask. I think, but the expectation and the conduct of education got to match. Okay, we all got to adapt to it. That's my personal view. Any more? There's one hand, on the right there. Yeah.
Yeah, I wasn't on this panel, but I'm going to take my last opportunity as an actual AI expert. Omar Yagi's perspective is very much aligned with how we think in the AI field, the way we develop. We think of ourselves as developing not just tools that you can download and work with, but rather a thinking style and a problem-solving style that you integrate into your workflow, and then you expand your workflow, and then you verify and you test and all that. So the scientific method is very much alive in the kind of loop that he's talking about. Our goal is not AGI or ASI or whatever. That is hype. That's Silicon Valley nonsense. I'm kind of sad that it's even come up here. If you told me that we didn't reach some mystical goal of AGI in 10 years, it was at a disappointment, I'd say no. We helped the Omar Yagis of the world to discover wonderful things. He's in chemistry, but think about healthcare, think about transportation, think about all the things that actually affect human life. That's changing right now in a revolutionary way. So that's really the goal. The other point I want to return to is the point I made about economics. There's not many economists in the room. But when you think about science, you don't have to worry as much about people stealing, cheating, trying to game you. In the real world, people do that all the time, and it's not because they're unethical. It's because they try to get value for themselves, their country, their family, and so on. And so economists worry about that problem of how can I ensure that you're telling me the truth if I go into a market and you tell me something that works? Well, there's reputational issues. There's things I can learn from watching the process around me. Markets have developed over thousands and thousands of years to support humans interacting with each other, even if they don't entirely trust each other. And if you don't have those kind of principles built as part and parcel of the AI enterprise, in addition to all the scientific checking and validation, the whole thing won't work. And that would be the disappointment to me, that thing just doesn't work. It leads to sacrifice, and it leads to systems working poorer than they should be expected to be. So it's a discipline that could take, like, chemical engineering, electrical engineering, 20, 30 years to roll out and start to show its value. And we're at the very beginning, as Omer says. But I just want to say, this is not my opinion alone. This is kind of the people who've been developing this now for the last 20 or 30 years.
That's Michael, right? Michael, I can barely see you, right? Yeah. Well, it's really reassuring to hear your opinion about AGI and ASI from an expert like you. So
it really is a term it's for the Silicon Valley venture capitalists. It's to feed this hype bubble that something miraculous is going to happen. I think people in this room kind of know that's not how science and human life works.
So this reminds me of, I'm old enough to have experienced 2 AI winters. This hype has always happened.
Again, that's AI is not the term we've been using. We've been calling it machine learning. And there's never been a machine learning bubble. Good. It's just steady progress.
Yeah. But anyway, this hype has happened before. That's what I'm saying. Yeah. Anyway, so a hand way back there.
Yes. I want to make a comment about the comparison which has been made between AI and the human brain. The first one is, of course, that the human brain is much more efficient in terms of energy consumption, as has been noted. But I think there is another characteristic which is essential, is that the human brain is feeling emotions. Emotions means that it's not only an electronic machine, but it has connection with chemistry, with the fact that it is connected with hormones, with a lot of molecules which make it feeling the rewards of what it is doing. And I think discoveries are based on emotions. You are doing physics or chemistry or biology because you are curious to learn about the world. You have the ambition to contribute to knowledge. You have a feeling, a connection with the world, which AI doesn't have. And I think this is also due to the fact that the human brain has been developed over billions of years of evolution, which has made it sensitive to things in the environment, which AI does not have, and I don't see that AI can have it in the future. At some point, it has been mentioned that Einstein discovered relativity through thought experiments. A thought experiment is something that you can do because you have an experience of the world and because you can see similarity between different kinds of events, which comes from experience, from the fact that you are connected to the world, that you have intuition, that you have a kind of feeling about what's going on outside. And I don't see how the AI can have this kind of quality. So my belief is that AI is a tool, is a fantastic tool, but it is not something which will be our boss when we do physics in the future. At some point, you mentioned the fact that Nobel Prizes have been given to AI. In fact, it was not given to AI. It was given to the people who used AI. I can give you as an example the fact that there have been something like 25 or 30 Nobel Prizes which were given to people who worked with lasers, but it is not the laser who discovered things. It is the people who used the laser which did it. My feeling is that AI, it will be the same with AI. I hope so, because otherwise we're in a big trouble. If there is a kind of general intelligence, if we are going to a tipping point where AI will dominate the creativity and the imagination of human beings, it will be very, very sad, I think, for civilization.
So if I heard you correctly, your answer to the question posed in the theme, which is, can AI discover anything, right? That's what the theme is. It sounds like it's no from you. Is that correct? I don't want to paraphrase you.
I think it will help making discoveries, as a very powerful tool, but you will always need to have behind that something which drives you, which is a need to know more things.
Okay.
And that's different.
Now, I know there are a lot of physicists sitting in the audience, Nobel laureates in physics. I asked a question about a thought experiment, which is if you had given somebody in 1905, but not Einstein, okay, the best LLM that they have, would we be able, as a human species, be able to discover all this stuff? That's the question. Sounds like your answer is no.
No.
I think that quantum mechanics could have been discovered by AI.
Aha, okay. And why
At least on the level of Bohr theory and so on. By enough observation, maybe not quantum mechanics, but the quantization would clearly be discovered by AI.
Okay. Yes, Brian, right? Brian? Yeah.
So with general relativity, I mean, one of the features of general relativity is that it kind of came out of the blue. We had the precession of Mercury. That was the only evidence of it, really. And I can see David disagrees with me, so I'm going to let him go through and answer why he thinks I'm wrong. But to my mind, AI wouldn't have had an easy chance to train on anything to make sense. So the measurement of things afterwards, spurned by Einstein's ideas, that allowed us to kind of better understand the theory. And eventually, maybe it would have come out, but I think it would have certainly taken a lot longer than what we have seen.
Okay. Not everybody agree. That's good. Can be from the audience. I think we should, yeah, please. There's a hand. The person in a white suit. Maybe you can say who you are and which organization.
Yes, I'm Professor Tangana from University of Free State, South Africa. I'm a mathematician, precisely fractional calculus. Just for people that may not know what is fractional calculus, you have what we call first derivative, second derivative. Then L'Hopital asks Leibniz, what if n is, for example, half? Then from there, we build what we call Liouville fractional derivative. And from there, we were able to build what we call Liouville fractional integral. And later on, there is a man called Capito that was working with a real-world problem. He came out with a new derivative. We call it Capito derivative. Now, as a student, when I was growing up, I noticed that we have two derivatives, but one integral. And I asked myself a question, how is it possible for us not to have an integral that is associated to Capito derivative? Because these two derivatives are different. I asked this question to many people working in fractional calculus. 65 years, nobody was able to answer the question. Then I discovered ChatGPT. And I asked the same question to ChatGPT. And ChatGPT told me that your question is very sensitive. And I convinced him to tell him that it is possible for us to have an integral that is associated to Capito derivative so that we should fulfill what we call in mathematics fundamental theorem of calculus. And that will help us to solve many problems. And with interaction between me and AI, I was able to introduce that integral. That actually, in our field, it is a breakthrough. Because the Riemann fractional integral that was introduced is using what we call continuous function, whereas the Capito derivative is used what we call differential function. So people that think that AI cannot discover something, I think that AI can come out with an idea that can change our world.
Can you, okay, you finished?
Yes.
Okay, I was going to ask you to summarize your main point in one sentence. So,
yes. So my main point is that I think that AI can make breakthrough.
AI can what?
I think that AI can discover something.
Okay, all right, so that's the answer. Yes.
So I think that the approach that Professor Yagi is taking is more typical of the way in which advances have been made in science. It really is a combination of theory and experiment and sequential approaches to things, where AI can probably assist on both sides of that, both in experiment and in theory. But it will be the question of whether it can on its own, which seems to be the nature of your question, go out and discover something because it has read the literature. It may be able to do that in some instances, but by and large, its main effectiveness is probably integrating it into the scientific process.
That's a good point. So Omar, let me ask you, Omar. So you've experienced this enough. Have you at some point said, God, maybe they don't need me? Can you share your thought on that?
In fact, the students designed 7 agents that do what I do in the lab. You know, talk to them, advise them, criticize figures, ask them to reprogram the robot, and so on and so forth. I was very impressed. I mean, I was very, very impressed. I mean, it's not as good as I am, obviously, but not. but it's pretty good. It's pretty good, and I like it because it allows newcomers to chemistry, newcomers to my lab to plug in very quickly without having to find somebody and coordinate with someone, network with somebody. Here they can really start on their own. So to me, that is a power we hold in our labs to bring in more brilliant minds, which many of them are not really choosing science anymore. So I think that this is going to revolutionize our ability to recruit into the sciences, because AI allows us to at least come close to operating in our labs at the speed that society is operating, okay? So that when students come into our lab, we don't have to send them back to the geologic age, right? Say geologic scale of everything is slow here, discovery is slow, and so on and so forth. So I think I am, as you can tell, I'm extremely positive about it. Of course, it's not, we are asking too much of AI at this point. We need to slow down and experiment with it thoughtfully so that it can get better and better and better. It's almost like raising a little child and teaching them how to walk or how to do things. Okay, they will get better and better with time.
I have one question to Professor Amr.
Yeah.
When are you going to have the AI interviewing your PhD students or your postdocs?
Yeah, it's a good question.
So if you have 100 applicants and you don't have the time to check all these CVs.
Well, I think that's already being done.
Oh, wow.
Yeah.
Yeah, there was another question. Yeah, there's one here and there's one here. I think this hand was first when I saw that, and then you. Okay.
Omar, would you have found the first crystals of the class of compounds that you study with the help of AI? Isn't it so that what you are doing now is repetitive and based on your earlier work?
I mean, to me, I don't even like that question because it's not relevant. It's not relevant. We have a new tool, and this new tool is going to, first of all, it's unanswerable because it's not, I don't know the facts of that, right? But we have a new tool. We're at a different stage of development of science. So let's use it to further the questions that we are trying to answer at this age of the development of science. I think that's the way we should be thinking about it. I don't think the question of whether it would have predicted the moth that was cited by the Nobel Prize Committee. I don't think that's a really important question here. I think the important question is that here's a nascent tool, nascent concept. We need to nurture it. We need to work with it. We need to set the ecosystem for it. And more people need to plug in so that it can get better and better. And by the way, one last point I just want to make is that science in general has been highly centralized, where you're basically the G7 are the countries that have few scientists, few countries, few scientists solving the world's problems, right? And we need to make it more distributive. That's what I also learned from AI, is that if it doesn't scale, if it's not distributive, it shouldn't, it's not going to be impactful. So I think that's another aspect that's going to change this question about the university structure.
Let me let the gentleman.
I want to make one point. We talk about AI all the time. What is AI? AI is a whole bunch of tools, not just one single tool. And we make mistake by summarizing this and even personalizing it as if it was some kind of a being. We're talking about simulation, modeling, prediction, machine learning, generative AI. It's one big bag of different things. And some of the dissonance that is here is really created because we're confusing one thing with the other. So I just wanted to suggest to make distinctions. What are we talking about? What is AI? AI is not some kind of one thing, a person that something like an uber person, some kind of a god. It is a whole bunch of tools, and depending on which tool we are referring to, we might have different opinions and different judgments. That's the point that I wanted to make. Thank you.
Thank you. We have 1 second, but maybe I can summarize a little bit. First of all, personally, I really enjoyed this discussion. I think we have a wide spectrum of opinions. We touch on a lot of fundamental issues. There are skeptics. There are people who are really enthusiastic. There are people who think we're in the beginning of something fantastic. People who think that if we had not invented quantum mechanics, AI could invent it. Okay, that's very positive. But there could be some theoretical limit, just like computing has. Ultimately, AI is computing, right? Have we explored that? I don't know. I'm not up to date on the theory of computability for AI, so to speak. At least the current approach. By the way, I don't believe the current approach is the only approach. The big data plus the neural networks. There may be many, many other possibilities. But anyway, no doubt it's a tool that we can all use in a very efficient way. We should make sure our students and so on use them. We should educate them in the right way. And I think the future is bright. So with that, let me close this and now pass on. What's the next session? I think this session is over now. Yes? Okay, we should walk off the stage and someone will come back on? Okay, thank you. Thank you very much.
Ladies and gentlemen, distinguished guests, the Disruptive Technologies Forum is about to begin. Please welcome Professor Dawn Freshwater, Vice-Chancellor of University of Auckland.
Good afternoon, everyone, or as we say in the Pacific, kia ora. A very warm welcome to this session this afternoon on disruptive technologies. And I thought I would just remind us of some of the comments from this morning, because it is quite remarkable that we are here together as a scientific gathering really focused on our integration with government, industry, finance, and a wide range of other important agencies. We heard from Professor Kornberg this morning and the Minister of Cabinet Affairs that disruptive technologies are reshaping the world, but of course that's much bigger than science. And so I do want us to draw back a little bit as part of this forum. Science is both being reshaped by disruptive technologies and is also the inventor of some of those disruptive technologies. So an important forum this afternoon, and we're going to hear from 5 of our laureates, followed by a panel of 3 young scientists who will shed light on how our world is being reshaped at speed. A few comments by way of introduction from me. So disruptive technologies are the emblem of our 21st century world. And while many see geopolitics as being at the forefront of global instability, we've heard in some of the panels already this morning that the disruptive technologies that we're talking about also fuel that instability. We've heard reflections on the notion of truth, trust, and future prosperity. The minister this morning spoke about a message of hope, what I might refer to as ambitious optimism, and we've just heard a comment about optimism. Reasons to be cheerful, you could say, and faith in humankind, which currently feels like it is somewhat fragmenting, and challenging us to come to understand better our experience as humans. Why are disruptive technologies so critical right now? Well, our communities are fearful. As a social scientist, I particularly bring that lens. People don't understand where this turbo state of technological change is leading and what it means for them and their lives. Furthermore, these disruptive technologies are often in the hands of people who many citizens believe are more powerful than their governments. This is the backdrop of this Disruptive Technologies Forum this afternoon. As I've said, we'll be joined by 5 laureates and we'll be joined later by 3 young researchers. I'm mindful of the steer that we've got this morning from Professor Kornberg, which was to focus on evidence into action and broad questions of social interests. So we'll discuss these in the context of technological discoveries. And a question to ask ourselves through this forum is there sufficient public trust in science and our systems to support the progress that we're seeing? With so much disruptive technology built on shared and mobile data sets, how do we reconcile concerns around data sovereignty that sit outside the scientific communities with our advancing of those particular disruptive technologies? Multiple commentators suggest we're in the midst of a global crisis, a series of interrelated crises, perhaps. And in science, basic science, while we can work to find those solutions to many of the crises, context matters, and it could be argued that science is in its own crisis. My concern and challenge is that technological solutions will not be the complete answer that our societies are seeking from us. They're partial solutions. Reshaping the world requires human relations, even if those relations are with and through technology. And those relations require trust. Stuart Haber this morning shared the notion of truth no longer being a given. And Omar just talked about sticking to the facts. All of this relies on trust. And so, colleagues, as we go into our panel and to hear our laureates, I suggest our scientific endeavours must be built on collaborations founded on trust. They must foster community trust and develop and implement mechanisms to recognise and respect and safeguard those communities. The demands on our scientists have never been greater. We hear it. Please do the basic science and make the discoveries, but hurry up and make it inexpensive. We want the solutions, but we also have quite severe demands on us. This is our context. Human progress can only be fully realised with citizen consent. This is our challenge, and now let's hear from our Nobel Prize winners on this challenge in the context of disruptive technologies. Our first speaker is Joachim Frank, the 2017 Nobel Prize for Chemistry, and his area of interest and expertise is around the imaging of biological reactions in real time by cryo-EM. I'm going to hand over to Joachim for his introductory comments, and of course we'll be moving through a series of speakers and going to our panel. Joachim.
Thank you very much. Yeah, I'd like to talk about a new technology, relatively new, which is essentially following reactions in real time. But in order to talk about this, I need to provide a context. The context is single particle cryo-EM. And what is single particle cryo-EM? It's a method that was introduced some years ago for looking at molecules, but molecules didn't need to be in crystalline formation, but they can exist at single particles. And the idea is that in order to get all directional information for a molecule, we don't have to tilt it. The molecule already tilts itself. It exists in many, many copies in a solution, and all we have to do is take many different shots and then figure out how to put the data together. So this was sort of a single idea that I've been pursuing for a few decades, and that finally got fruition. And nowadays, it has, I believe, revolutionized structural biology. So nowadays, we have a structural determination workflow that goes all the way from protein purification, negative staining, specimen vitrification, data acquisition, and so forth, all the way to model building. And what is new most recently, a few weeks ago, is that atomic models can now be built using machine learning in the context of existing experimental data. So this is not like AlphaFold. AlphaFold rests on the knowledge that has been gained in decades of model building, but rather it is now a way of combining machine learning together with constraints provided by experimental data. So what has been achieved by single particle cryo-EM today, I only give a few examples that where my laboratory has made contributions, but in fact now thousands of structures are being solved experimentally by this method. So what is missing? Missing is really the dynamics. I'm showing you an example of dynamics that has been inferred not by some kind of following reactions, but rather by stopping reactions at known times by chemical means. And this is sort of, I would say, it's essentially cheating. We are not really providing dynamics, but we're stopping the reaction, and we don't know what kind of artifacts we introduce. And this is an example here from the early times when we wanted to know how the ribosome makes proteins. So we were able in 1998 to put together the entire workflow of the elongation cycle. But this is, as I said, cheating because it was done by using GTP analogs and antibiotics. And so right now I'm talking about starting and stopping reactions in real time using a microfluidic chip. And you can see the diagram there. The idea is we are mixing two components very fast within a millisecond or a half a millisecond, and then we have a reaction channel, and the reaction channel defines the time during which the reaction takes place. And at the end of the channel, we have a sprayer which is gas-assisted, and it sprays the reaction product onto the grid as the grid falls into the cryogen. We switched over from silicon chips to PDMS-based chips in order to be able to develop them faster and make them applicable in many different situations. And you see a diagram here. Changsong Feng is the person who contributed in great amount to this effort. So the latest example is a ribosome subunit association, which takes place essentially within a second or a fraction of a second. Ribosome subunit association is the basic function. It's part of the initiation, and during this time, the subunits find each other and associated to become a working ribosome. And we were able to follow this in real time, and we can exactly infer how the subunits come together and how the bridges form. And due to the lack of time, I cannot go into the details. So we can see how within 10 milliseconds the first association takes place, and then the exact configuration of the ribosome forms. Okay, thank you.
Thank you, Professor Frank. Now we're going to hear from Kurt Wuthrick, who is 2002 Nobel Prize for Chemistry. Over to you, Kurt.
I have a single slide which doesn't show. Never mind. My first disruptive technology contribution is to use the belt of my reserve pair of pants instead of slides. Our daily life relies on the function of a large number of different molecules: DNA, RNA, proteins, lipids, sugars, and so on. Structural biology unravels the mechanisms underlying these functions, as we have just heard in the preceding talk. Here, I want to illustrate this with one class of these macromolecules, namely proteins. And the theme that I want to address is in some way related to what we heard earlier today from Michael Jordan. When he talked about alpha-2, he mentioned the boundary problem. And what I want to talk about is how will we move boundaries? Will AI move boundaries, or will new experiments move boundaries? I'm convinced that it is new experiments which will then again provide information with which to train new algorithms, and so we will go step by step in this way. My belt serves to illustrate that proteins have a very simple chemical structure. They are linear arrays of building blocks. The start is defined and the end is defined exactly as in my belt. I can in no way understand the wide range of functions by proteins if I know only the chemical structure. I give you two examples. A common structure in proteins is the so-called antiparallel beta sheet or a hair needle structure. In a hair needle structure, the strength of the polypeptide is comparable to steel. It's very hard. Another common structure that we find is the alpha helix. If we pull, there is no resistance. And that is what we find in our hair, for example. If we had the same in the ligaments in our knee, it would be a disaster. When we talk about drug development, if I only knew the chemical structure, I could target sequentially following residues in the structure. If I know the three-dimensional structure, then whenever there is a crossover in the three-dimensional structure, I of course get all of a sudden recognition points that are far apart in the chemical structure, and now all of a sudden form the receptor position where a drug can bind. So with this, I hope to have illustrated to those of you who are not in the field why it is important to know not only about the chemical structure of proteins, the same applies to DNA and RNA, but that we need to know the three-dimensional structure. How are these structures determined today? We have just heard a very nice example, cryo-EM, how proteins are isolated, purified, put on grids, and then frozen into liquid nitrogen. That's a very low temperature. If you use X-ray crystallography, you grow crystals and put them into liquid nitrogen at very low temperature so that everything gets rigid and can be observed in high precision. The technique that I use is nuclear magnetic resonance spectroscopy. There is a small step toward the real system in which we are interested. We can work in solutions that resemble body fluids, but this technique is limited to relatively small molecules. I'm talking about small proteins, not really small molecules, and we have, therefore, also the limit of low sensitivity. Now, when we work with the structures that have been determined for the isolated, purified proteins, we are limited. That is a very important boundary. I live this in our daily work in providing input as a basis for drug development. We use the structures, all kinds of structures that have been determined from isolated proteins, and we use these in combination with function assays of the same compounds that are performed in living cells or in higher organisms where we have a myriad of additional molecules in the solutions or attached to membranes that may influence the functioning of the proteins of which we have determined the structure outside of the living mechanism. Therefore, the outlook for the next decades is that structural biology will move toward being able of studying the behavior of the biological macromolecules in vivo, in living cells, and hopefully in higher living organisms. We are at the very start of this today. I mean, we have cryo-electron tomography. which provides us initial pictures, but at very low resolution. We also have NMR spectroscopy with living cells, which can give limited information today about the structure of proteins inside the cell, and more importantly, about interactions between molecules in the living cells. And we also have the possibility, which has been very little exploited today, to combine NMR spectroscopy that will provide us about information on structure and interactions with magnetic resonance imaging, MRI, that many of us have experienced in medical diagnosis. And there we can combine the information from spectroscopy with geographical information that we obtained from magnetic resonance imaging. This all is at a very early stage, and I see the future of the contributions from structural biology in development of methods that will improve these approaches, both by cryo-EM tomography and by magnetic resonance techniques combining imaging and spectroscopy. Thank you.
Thank you, Kurt. Thank you. Now, I'm going to move on really quickly. I'm keeping the introductions very short because of the time. Prof. Tao Zhang. Now, Prof. Tang is a researcher at the Dalian Institute of Chemical Physics and a laureate by citation 2025. Over to you.
Right. Can I have the controller? Can I have the controller?
Could we have the slides? Thank you. Thanks.
You don't have a presentation? Yeah, I have. No, you don't have the presentation.
Do you have a belt you can use, Professor Zhang?
Could you upload my presentation?
Do we have the slides? If not, then we may.
No.
Can you manage without them?
Yeah, I provided my presentation PPT to the conference. So probably you can, the next one.
We'll move on and then we'll come back and see if we can find the slides. So we'll go to David McWilliam. And David is a Nobel Prize for Chemistry 2021. David, over to you.
Do you have the clicker? All right, do you have slides for me? Yeah, I do need slides as well. Thank you. All right, and I guess I've got an extra minute and a half, hopefully. So I'm going to try and convince you a little bit about the value of photons for chemistry and biology. So many years ago, myself and a few others had the idea of, would it be interesting to take the knowledge from inorganic chemistry, and specifically the idea of taking the knowledge of how to power the planet with solar energy, and take that chemical knowledge and translate it and export it into organic chemistry. We did that, and it led to this area, which is now known as photoredox catalysis. So photoredox catalysis, apart from the fact that it allows you to perform these really beautiful reactions and make some really nice videos along the way, it actually became a reasonably significant field over the last 20 years or so. So the initial papers in this area were published back in about 2008, and then last year, and between last year and this year, this will be well over 1,900 papers in this area. So the question is, why is it that taking that knowledge from inorganic chemistry and photons and moving it into chemistry, why did it become interesting to academics, but more importantly, why did it become interesting to the industrial world? Well, it became interesting in one way because it allowed the development of many new organic reactions, and many of those new organic reactions can power the development of new drug molecules and new types of drug molecules along the way. And these are just some of the companies who've actually been involved in doing this. I'll just show you one example. This is a relatively recent one, but from Novartis. This is a Rho kinase inhibitor, which is used in neuroscience. And the blue circle, which is on that molecule, is a bond that previously would not have been able to be made readily without the use of this new technology. And this is just to demonstrate that one of the kind of beautiful aspects of this is that you can now perform these chemical reactions on scale, actually using, this is blue light, this is visible light, being performed at Merck Process Chemistry in Rahway. But I didn't want to really talk to you mainly about chemistry. I really wanted to talk to you about how you can use photons in catalysis and use it to gain new insights into biology. But one of the key features here is the aspect that all the chemists around the world, in both academic and industrial settings, are now effectively have the infrastructure to perform photonic chemistry. So they can now use this to actually start to probe questions in biology at the same time. So what are the areas that this is being used for? So one area which has gained a lot of attention has been for biological interaction networks, or otherwise known as interactomes. And for those of you who don't know this, if you think about any biological molecule, for example, a protein of interest, most biologists can tell you that those molecules are constantly interacting in a dynamic fashion with lots of other molecules, whether it's other proteins, whether it's other metabolites, single molecules, signaling molecules, nucleic acid-based systems. And what's really interesting is the vast majority of these interactions are actually not known, and that becomes really important if you're thinking about disease state biology. So one of the questions becomes, how do you identify these interactions? So one of the ways that we started to think about this was, can you use proximity labeling? And the idea is, can you put a catalyst on your biological molecule of interest, for example, a photocatalyst, and then shine light on it, and now let that protein of interest go about its usual business, but now it will leave its footprints wherever it goes. It'll start to label everything it interacts with. So the applications of this become quite manifold, and this is just an example of being able to use this. These same photoreactors that were used for chemistry are now being heavily used now for doing this, for biology or for gaining insights into biology. So what are some examples of that? Well, this is one example. This is Herceptin. Herceptin is a well-known medicine for HER2-positive breast cancer. However, 70% of patients have primary resistance to this. But what you can do is you can put the photocatalyst on Herceptin, and you can simply map the biological differences between the two different states. And you can start to determine the biological reasons why some people are susceptible, yet other people are resistant. And thereafter, we've now been able to develop a small molecule drug which allows you to now switch on Herceptin for cells that were previously resistant. Other things you can do, for example, is you can take the brain and you can actually start to think about ways to find small peptides that actually cross into the brain. And we've now been able to identify completely new receptors that allow small peptides to get into the hippocampus, and do this selectively using receptors that were previously unknown. So the value of this is a bit like the metaphor of thinking about a small tugboat that can effectively drag an ocean liner into safe harbor, meaning that you can take these really small peptides now and they will effectively drag things like Taxol and even much larger molecules like antibodies into the brain based on a very small peptide sequence. But other aspects, just to sort of finish off with, has been in the neurodegeneration or the neurology area. One area in particular has been around studying TDP-43, which is heavily associated with ALS. And we've now been able to sort of figure out some of the key signatures that not only govern assembly of TDP-43, but also disassembly of it at the same time. So this, again, has gained a lot of attention. We actually recently entered into a pretty significant 10-year agreement with Johnson & Johnson, who have now, they're industrializing this technology, but all of these other companies are also working heavily on this, as well as Pfizer and Merck, which is obviously something that we're quite excited about. And I'll finish off by acknowledging, these are the folks at Princeton, many of them did this work, and lastly, thank you for your attention.
Thank you, David. Now we'll go back to Professor Zhang, if you're ready. Perhaps, Professor Zhang, are you ready? No, keep going. Okay, we'll go then to Kip Thorne, who is our Nobel Prize in Physics from 2017. And Kip, I'm going to invite you to start speaking straight away. I'm mindful that time's ticking away.
Thank you. Can you bring up my slides, please? In the 10 years since LIGO first detected a gravitational wave, we have improved our detectors so that several times each week, LIGO sees waves from colliding black holes. To achieve several per week, we use radically new squeezed vacuum technology, which is also called squeezed light. In this talk, I will describe in greatly simplified form how we conceived and perfected squeezed vacuum technology. It was a 50-year struggle, mostly in American universities with government funding, and in year 44, it began triggering spin-off into private industry. I'll conclude with comments on the danger that political turmoil in America may be destroying this university-based route for creating new technologies. In 1972 and 73, 3 foundations were laid for squeezed vacuum technology. The first foundation was when Rainer Weiss at MIT invented the gravity wave detectors that we ultimately would build for LIGO. In this simplified model, 2 mirrors hang from overhead supports at the ends of perpendicular arms. A laser beam shown in red monitors the difference in arm lengths by interferometry. A gravitational wave stretches and squeezes the arms oppositely, so the mirrors move in and out, and due to interference of the light, the output signal light brightens and dims. The second was that upon learning of Weiss's invention, Vladimir Brzezinski in Moscow warned us that the gravitational waves might be hidden by the mirror's quantum fluctuations, a tiny shaking, a billion times smaller than an atom that can never be stopped. To conquer this mirror shaking, Brzezinski said that we must create some sort of quantum technology. Third, the key to that technology, vacuum fluctuations, was laid by another Russian, Yakov Zeldovich. Imagine a box filled with nothing, only a vacuum remains. The vacuum is filled with tiny fluctuations of everything that ever could reside inside the box, vacuum fluctuations. Zeldovich speculated, and he was probably right, that the Big Bang explosion that created our universe produced only vacuum fluctuations and nothing more. But those fluctuations, by feeding off the energy of the universe's expanding space, transformed themselves into all the matter that fills our universe today. Now, these 3 foundations were followed by a decade of frustrating gestation. From 1973 to 1981, Brzezinski and I and our students struggled to invent a quantum technology that protects the gravity wave signal from the mirror's quantum shaking. We found nothing very promising until one day in 1981, my student Carlton Caves had a brilliant insight. Vacuum fluctuations of light entering the interferometer backwards can control the mirror's shaking, Caves realized. In technical language, the vacuum fluctuations, by beating against the laser light, create fluctuating light pressure that controls the mirror's quantum state. Perhaps Cave speculated, just as the Big Bang manipulates vacuum fluctuations to create all our universe's matter, similarly, we humans can manipulate vacuum fluctuations so that they do what we want, prevent the mirror's quantum shaking from hiding gravitational waves. And Cave figured out the precise manipulations to do that. Squeeze the vacuum fluctuations, reduce one aspect of them while increasing another in precisely the right way, a different way at different frequencies. In 1983, Jeff Kimball invented a powerful technology for squeezing the vacuum. In technical language, send the vacuum fluctuations through a carefully tuned laser-pumped nonlinear crystal, and then through a long filter cavity. Next came a 36-year struggle to build and perfect Kimball's squeezer, make it strong, accurate, and robust. Kimball at Caltech worked the problem for a decade, and then LIGO research groups took over at MIT and in Germany and Australia. And finally, in 2019, a simple form of squeezing was mature enough to be implemented into LIGO. Almost miraculously, this brought a 50% increase in detections of colliding black holes, signals that had been hidden by the mirror's exceedingly small quantum shaking. Seeing LIGO's success, private companies then embarked in 2019 on implementing squeezed vacuum technology into their own technologies. Xanadu for photonic quantum computing, and with DARPA impetus, miniaturized squeezers to use in gyroscopes and magnetometers for navigation. In the meantime, in 2023, LIGO implemented a more powerful variant of squeezing, bringing us to several black hole collisions each week. This history of squeezed vacuum technology is similar to that of some other radical new technologies. Foundations and then gestation in American universities, often with international stimuli. The technology, with risk of failure, is brought toward maturity for 10 or 20 years or more in universities with government funding, and then private companies then and only then see the possibility of profit at acceptable risk and begin investing heavily. Just a moment. The Trump administration's attacks on American universities are endangering this route for new technologies. Alternative routes are needed, preferably routes with strong international collaboration, so that no nation can gain an advantage by single-handedly bringing a powerful, disruptive new technology to maturity. Thank you.
Thank you, Kip, and I think you were concluding there some of the points I was making about the potential crisis in science and the lack of trust in science that we're starting to see at government levels. We're now going to go back to Professor Zhang. I think you have your slides ready to go.
Okay. Ladies and gentlemen, it's my honor to talk a little bit single atom catalyst, a new frontier materials in the chemistry. So, overview of the single atom catalyst, catalysis play a very important role in our society, particularly with catalyst, we can produce a fertilizer with food, and we produce polymers, so we can have enough clothes. So, catalysis is very important. And before my work, for the commercialization catalyst, normally with nanoparticles, cluster, and sometimes also with single atom. But it's a mixture, so people don't know which one is the actual size, nanoparticles or single atom. So about 20 years ago, I discussed with my students, try to design a new kind of catalyst, which is all the single atom was on the support, was isolate on the support. So with such kind of catalyst, can we find some new chemistry? So after a few years, we are very successful. So we published the first paper, the single atom catalysis. We coined a new concept in 2011. We gave a clear definition about the single atom catalyst, which means the core metal atoms will separate each other and only interaction with support. Now, this kind of new concept is very popular and receive much attention from the society. The paper ranking the #1 most cited research paper in Nature Chemistry up to now. And after our work, you can find a lot of paper published. Although we begin from the noble metal, now almost all the important metal in the periodic table was reported to be a single atom catalyst. And you can find up to now more than 50 reactions was reported to use the single atom can obtain very good performance, not only activity, but also the selectivity. So you can find from 2011, after our work, there are 20,000 papers was published in this field and more than 1 million citations in this field. So single atom catalyst has become a most active topic in the catalysis. Actually, not only catalysis, but also in the whole chemistry and materials and also other fields use the single atom catalyst concept. And in the world, more than 100 countries and more than 1,000 research groups follow our new concept, the single atom catalyst. And the Chemical and Engineering News highlight our work, top 10 achievement in chemistry in 2016. And last year, I'm very happy to receive the citation laureates and for the similar contribution to the single atom catalysis up to now. 89 citation laureates go on to Nobel Prize. So you can find for the conventional, traditional catalysis, we have many important concepts. And during the last 33 decades, you can find many important concepts for the nano catalysis. Now, with our single atom catalyst, you can find people can understand catalysis from micrometer to nanometer, and now we can to atomic scale level. So the single atom catalysis is very important. It's one of the reasons to receive so much attention. So now we try to use artificial intelligence. Before, because nanocatalysis is a mixture, it's a nanoparticles, cluster, single atom, so it's quite difficult to obtain reliable data. Now with single atom, it's possible. And also with a single atom, we can obtain clear structure activity data and the spectrum structure data. And we learned from the Nobel Prize in Chemistry 2022, learn from the protein prediction. So now we can predict our original design of our catalyst. This is some advantage and disadvantages. I don't have time to give more details. So now in our laboratory, we try to set up such kind of data, big data, to try to establish the structure, spectrum, and the reaction database for single atom catalyst. So some opportunity and challenges. Now the synthesis is very important, particularly atomic manipulations challenges, and characterization is also very important. And also we need time to understand the physical and the chemical origins, and also the theoretical understanding of the original design of single atom catalyst is very important. For the commercialization, there are many processes has report to use the single atom catalyst, and particularly for the energy conversion reaction, you can find the water splitting, carbon dioxide conversion, and nitrogen activation use our single atom catalyst. So single atom catalyst play a very important role for the carbon neutrality in the future. So summary, the single atom is a very hot frontier concept in catalysis, but also in the chemistry and the materials. Single atom catalysts provide atomic scale understanding in heterogeneous catalysis, regional design. Try to combine single atom and artificial intelligence is very possible. And commercialization important. Green hydrogen production, carbon dioxide conversion is very promising. And particularly because the single atom, we have used autumn every autumn. So autumn efficiency is very high. So catalyst will be low. So low cost single atom will play very important role in the carbon neutrality. Thank you very much for your attention. Thank you.
Thank you, Professor Zhang, and thank you to all of our laureates for their thoughts on reshaping the world.
Thank you.
And a reminder, it's around atomic manipulation to interstellar exploration, so we really have gone the full spectrum. Now I'm going to invite the three young scientists to join me on stage, and we will have a short panel introduction to the disruptive technologies of those young scientists, and then we're going to open to questions. So once again, reshaping the world, and we've heard from our laureates on the work through disruptive technologies that has happened at the atomic level, the interstellar level for reshaping our world. And we're going to start by introducing our panelists and asking them to talk a little bit about what they're doing at the moment in terms of their work reshaping the world, and to think about the disruptive technologies of the future. So we have with us Rahul Nair, who is the Blatnovic Award for Young Scientists from 2014 and 2024. And we're going to hear from Rahul shortly. He was also selected as the Blatnovic Laureate in Physical Science and Engineering recently, a couple of years ago, for his work on two-dimensional materials-based membranes and addressing global challenges. We have with us Moran Berkovici, who is the 2019 Blatnovic Award for Young Scientists. I'm interested to hear about the Lab on a Chip, which is one of the areas of work that you've been involved in, and Samuli Oti, who is the 2023 Nicholas Curtis Science Prize for Europe, as well as the 2020 Young Scientist Prize. And when I read about Samuli, I found that he's interesting questions such as, what does it feel like to touch quantum physics? So I think we're in for an interesting panel discussion. I have encouraged them to be disruptive, as that's the theme. So it's not just disruptive technologies, but also to be provocative in their responses. So first question to get us started is, so what are you doing in terms of reshaping the world? Let's start with you, Rahul.
Good afternoon. So myself working on graphene. So as you all know, probably graphene is the thinnest material, and it has many applications ranging from electronics, battery technologies, and so on. So myself particularly is working on developing graphene-based membrane for different separation technology, including water desalination and separation for industrial application, making pharmaceutical filtration, and so on. So in terms of disruptive technology, like as you know, graphene has, of course, if you are using electric cars, they are already being used in the battery. So it's really disrupting several sectors, not in one sector. So like energy sector or even water sector is too early, it's still under development, it's still in the pilot scale testing and so on, it takes time. And then there are other sectors like composites and telecommunication sector and so on. So there are many scope applications there in this area, and this is what myself working in that field.
Thank you. Let's move along the panel. And so, Moran, where are you changing the world and reshaping the world?
So, sorry to disappoint, but I will not talk about Lab on a Chip. So Lab on a Chip was indeed the award, the Blavatnik Award, a few years ago. I'll say briefly, since you brought this up, the concept of Lab on a Chip has existed for about 30 years, and we as a community had totally failed at it. There are no labs on a chip, there's best protocols on chip, and we're trying to change that through real-time reconfigurability that will bring labs to be something, lab on a chip, to be something closer to what is a real lab, where we don't a priori know what is the next step. We're not just running precise protocols, but we can actually make real-time decisions. But I leave that aside, and I'll tell you about a story that actually started here in the World Laureates meeting in 2019, where a random conversation brought me into the world of creating optics with liquids. And so one of our major projects in the lab is trying to create giant space telescopes using liquids. And so Hubble Space Telescope, about 2.4 meters in diameter. The James Webb Space Telescope, 6.5 meters in diameter. An amazing triumph for human engineering. But if we want to go larger and do things, for example, look at exoplanets, so depending who you ask, but be on the order of 100-meter telescope. There's no technology that can create something like that on Earth, and even if there were, there's no way of bringing something like that to space. The current methods of folding that have served James Webb just do not scale there. And then my expertise are in fluid mechanics, and liquids fold really well. And so bringing liquids to space is relatively easy. And the question that we try to answer is, can we then use the liquid to give it a functionality? And one of the functionalities that we seem to be able to is to create shapes of mirrors, of telescopes. This is now a collaboration with NASA under a NIAC project. The current working point is a 50-meter telescope. There are a lot of challenges to make this a reality, from a fantasy to a reality, of having liquids that do not evaporate in space and having them reflective and so on. But it seems to be feasible, and maybe on a 20-year time scale we'll be able to get there. If I may, one more word to put in, then if we can do that in space, this is all based on surface tension and weightlessness, but we can actually bring that back to Earth. And getting rid of gravity on Earth is actually also very, very easy, also using liquids, so simply neutral buoyancy, jumping into a pool. And so if we get rid of gravity on Earth, then in the lab, we can create eyeglasses from polymers simply by ascribing the right boundary conditions on the liquid, and we can create any lens with any spherical, cylindrical correction, and skip the machining, polishing that is currently done for traditional lens manufacturing, and bring lens manufacturing to low resource settings to the developing world. And that is the conversation that started here with David Zilberman back in 2019.
Thank you, Marinus. And Samuli.
Thank you. Yes, as it was described, my research work is rather kind of distant from the everyday experience, and but then I thought that maybe I would take a leaf out of the book in my kind of other occupation as the chair of Young Academy Finland to connect this better to also the topics of this meeting and the ongoing other meeting, which is at the same time, which has to do with policy and decision making. And so this session is about disruptive technologies. So where do these typically, or at least often, come from? Well, they come from fundamental discovery in science, but it takes a long time. I mean, if we look at the Nobel laureates in this room, discoveries of whom many of them led to disruptive technologies later on, but it may have taken decades. I mean, it may take a decade or a few to get the prize in the first place after the actual work was done, and then it takes even longer to move on to the technology stage. And so that is important from the policy perspective, because one then arrives at the conclusion that, well, technology for these people isn't actually a good, at least on a kind of personal level, a good motivation for the work that was done. At least I can speak for myself here. If my work ever turns into some useful technology, it was not because I wanted to create technology, but because I enjoyed the discovery. And so then, why is fundamental science so slow? Well, let me pick one phenomenological example. Many people probably recognize that it often takes a seemingly unrelated tool developed in some very different context to be or maybe observation from some very different context to be applied to your specific topic, so it can advance beyond what we would call a fundamental problem or a fundamental question. And so then if we think about, let's say we wanted to promote this sort of discovery and activity, well, pouring, let's say, funding on a spot, I want a quantum computer, give me a quantum computer. Well, if quantum computing in this sense is a fundamental problem, we don't know whether it is, but if it is, then it's actually possibly not going to be accelerated by this on-spot funding if we need to actually fund some very different thing that would be then applied to solving the problems in quantum computing. And so then finally, I come back to the work that I do, which is fundamental research, and all of this freedom that I'm trying to paint for us here. Well, it comes with responsibility. Integrity is needed. And okay, I don't work on quantum computers, but that's perhaps the closest kind of very well publicized field to what I do myself. And I do feel that physics in general is being harmed by the hype and the false promises made in that context, in many cases to win funding from somewhat untraditional funding sources for fundamental research. Thank you.
Thank you, Samuli. Now, three very different perspectives from our young scientists on the panel. We have just under 15 minutes. I'm going to turn to the floor to see if there are any comments or questions, observations from our 5 laureates, just to start us off before we go broader. If you can put your hand up so that we can see you if you have comments or observations. A question for the panelists. Not seeing anything from our presenters. Anything more broadly around the room, around the table, as a follow-up to what you've heard?
About a question from audience.
Questions to the audience. There's somebody at the back there.
Yeah.
Thank you. Could you say who you are?
Sure. This is Felix. By training, I'm an AI scientist based in New York. I work on the language model, next generation multimodal language models. So I'm AI pilled, so my questions related to AI as well. My question to the panelists and laureates are, in your field, do you foresee how big of a role that AI will play in the next 1 or 2 years? And a part 2 of this question is, what types of scientific problems or sub-problems in your field is fundamentally out of reach for AI, for the current AI system to be able to solve, even given massive data and compute? Thank you so much.
Who would like to start?
I can try. I'm not an AI person. I am an AI user, maybe the most basic academic user. But the approach we take in the lab is very much the one that Omar Yagi presented before, which is it's an accelerator, right? And so we're driving it, but it's our best pal. And what I actually see it's the excellent users, the excellent students, are getting even better when they can leverage this tool. And so even things like you derive an equation, you do your scaling, you simplify it as much as possible, you get to this equation that you think is probably solvable. Someone solved it before. In the old days, meaning 2 years ago, you would go to the library and look for the book with the right equations, and now it ends up in a line because it will direct you to the right solution and so on. And so it just really accelerates things a lot.
Mm-hmm.
Maybe I
Rahul?
can add one point there. In terms of research, we are working on advanced material. So we have so many materials, endless new materials are coming. So I think AI can definitely help in screening them faster than what we used to do manually. And not AI, maybe machine learning can help in terms of simulation and so on. Defining, a predefined material or designing new materials faster than what it used to be. I think that is what probably can help in the coming decades.
I could add to that from my own perspective. That's so it depends a little bit on what you meant by this question, or what perspective you meant. If I think of, I don't know, writing analysis code or doing literature research on some concept that we want to apply to what we do or something, then AI or language models or machine learning is totally applicable to everything that we do. On the other hand, if you're asking from the perspective of some sort of like dominant source of, take and apply kind of instructions on how I do my research, then it's applicable to nothing. Like if I exaggerate a bit. So it really depends on the view you take.
I think a second part of the question was related to what's out of reach in relation to your own areas of development and disruptive technologies. What are you seeing that's out of reach, and the relevance of AI to that? But I might extend that, because all of our laureates today, when they were presenting, were talking about disruptive technologies and advances at the context of cross-disciplinary boundaries. And it's ordinarily thought that innovation takes place at the intersection of some of those disciplinary boundaries. Could you say something about what might be out of reach and what crossing those boundaries might lead to? Because it seems that we're having to do much more of that. There are more and more emerging disciplines, of course, that's what we're hearing about, but also the innovation that's taking place through the disruptive technologies is boundary spanning, and how that might help to achieve some of those out of reach, out of sight things that we're talking about for your areas.
Yeah, well, normally interdisciplinary is very important for breakthrough technologies, but they are all rooted in single discipline. Most of the time, all these technologies are coming from fundamental research, as we said before, and these are actually rooted in one discipline. But it becomes a disruptive technology when other people work together, and when we find applications in other areas and working together, then it becomes a disruptive technology, right? So it's fundamental breakthrough science is important, but when it comes to outreach, I think you were asking specifically, outreach is more into the technology, technology, and then that's very important. Probably AI can also help in simplifying the technology to translate into the common people. So I think that their AI can help us in making it into a layman much better than what we used to do.
Just on that, Rahul, we were challenged this morning, actually, by Professor Kornberg to think more about that translation. We talk a lot about translation. We think we do it well, but we speak to the audience as if it were us. So, when you're talking about that translation and the disciplines helping that translation, do you see that as a fundamental responsibility still, or do you think we can leave that to technology?
I don't think we can leave that to technology. Definitely, we need fundamental science. We need to work together within the disciplinary. In the scientifically, it should be rooted, rather than leaving into innovators and industries.
Moran, your thoughts?
Yeah, I just think it's not a clear line of whether you should or shouldn't. What's so nice about academia is this breadth and gradient of people who work from very fundamentals to very applied and anything in between. And I don't think that someone who's a complete, let's say, theoretician must think about the applications translation of this. No, I think they should talk to enough people so that there is the next person who is somewhere in between, and the next person, so on, the way it basically worked until now. So yeah, I think there's some responsibility, but not for everyone to jump into translation. And I'm saying it as a technologist. Very much.
Samuli, you mentioned integrity and responsibility actually when you were just opening. And so I'm interested in your thoughts on that as well, because it relates to the comment this morning about how we bring our cultures together.
How do you bring, sorry?
Cultures together. So government, industry, economists thinking about finance and scientists, and the responsibility there on our part.
Well, I mean, this is a very kind of a scientist answer, but the way I've, at least in the past, tried to explain this is that the scientific enterprise, maybe universities facilitating it, it's a fragile thing, and you need all of these structures taking away external pressures for this like honest, or at least most of the time honest, pursuit of, you know, the truth to be possible there. And if you take that away, you know, it doesn't have to be anything more like kind of malicious than somewhat unconventional funding schemes. And then it's already very close to the point where this like trustworthiness is no longer there.
So I'm turning over to the audience. We've got a few minutes left. A final comment or question to the panel, or maybe the panelists have a question for our laureates that spoke. Thank you.
So I learned many years ago that sociologists who study how science gets done, and in particular where true disruption comes from, contrast what they would refer to as the lone hunter-gatherer scientists who just follow their nose, follow their curiosity, and are willing to be heretics and not listen to the crowd, versus sort of the communal harvester scientists who really do a different type of science, a very important type of science, but often driven by access to technology and resources. And you can see the complementarity, but of course the danger of the communal harvesters is that they adopt herd mentality and they go off in one direction, and then you don't leave space for that real creative heretic who maybe is the person who's going to make that big discovery you're waiting for. And my physicist colleagues will tell me if I have the quote attribution right, but there's the Max Planck quote that, you know, progress happens one funeral at a time. And as we're having these discussions, I mean, AI is not going to die. So, I mean, there is the danger, it seems to me, that it's going to sort of immortalize ways of thinking and quote-unquote truths that maybe in some cases aren't really true.
Well, I mean, I don't know whether I'm answering this question at all, but one thought that arises is that I'm personally compelled to try to kind of keep at bay this typical Western, at least Western thinking that you know, major discoveries are made by and only by like individual geniuses. I mean, this is a little bit provocative statement, but I mean, I would encourage people to think of the opposite possibility, which is that it was, you know, pick your favorite discovery, I don't know, theory of relativity, for example. It was the right time for this discovery, and somebody else would have done that. Maybe it would have taken 10, 20 years longer, but on like geological scale, that's irrelevant. And maybe also on the kind of like population statistical scale of understanding what the process of science actually is in its core, it might also be irrelevant.
Any other reflections?
Maybe I'll just jump in and say that I think we should be careful, you know, of directing science in, you know, one way or the other. And you know, maybe it's a cliche, but it's really on the diversity of it. And sometimes it comes by a group, and sometimes it comes by an individual. And I would even say, you know, we emphasize so much how much basic fundamental research is important for innovation in a way that we cannot predict. But I also, you know, I like to promote technological fantasies as a way for example, the things that we're doing. I'm very much a technologist. I used to be, shy about it, especially to an audience like this. But no, it's a fantasy we pursue. On the way, there are scientific questions that come up. Sometimes we even manage to answer them, and that creates new things on their own. So just the diversity of it.
Rahul, anything from you?
Not on this one, but one comment, because we are running out of time. We are talking about trust on breakthrough technology. One thing is, if you look at the history, like once several years back, polymer technology was a breakthrough, disruptive technology. Everybody liked it, but now the society is worried because they are affecting ecology, health, and all this kind of thing, and that probably causing some of the worry rather than trust on this new technology. I think that's also we need to address. Today's breakthrough may have some problem after several tens of years and things like that. So that's maybe something we should discuss and find a solution for that as well.
Mm-hmm. I had a thought when I was listening to your comment about this, which was really less about the individualist versus the community approach and more about the concern I would have if there was an absence of doubt and skepticism. And I think that's come up a few times today. And I would hope that through our panel at least, and through some of the conversations that we're having today and tomorrow, that will start to crystallize a bit more, because with the absence of doubt and skepticism here, then we are almost in a self-fulfilling prophecy. So I think it was, for me, that was my immediate response to the points you were making. We're out of time. Can I thank the panelists here this afternoon, and also once again thank the laureates who presented keynotes. I know it's been quite a long day already, and so I'm sure everybody's starting to feel it, but thank you for your inspiring words and contributions.
Thank you.
Distinguished guests, we will resume our sessions in 10 minutes.